guess I'll start now. It's 2 already. So, first of all, welcome everyone to the seminar series. So this is obviously almost one of our largest events that we as a math club are organizing, and I hope that a lot of younger students have shown up, and I hope that this will be of great use to especially the younger students, because this will be a very good window into the work we do as third and fourth year undergraduates and some fifth years as well in the summer. So it will give you an idea of like what kind of new math is out there, and yeah, I hope everyone can take something out of each and every talk, even though some of them may be a bit advanced for you and even for us as third years. So yeah, I'm out of campus unfortunately because I'm on medical leave. So, but I hope to be tomorrow physically. Let's see. So yeah, so I'll start with my presentation. So I will take questions at the end, if any. So my presentation is on the Kakia set problem. So this is something I worked on during my summer as a part of PSRP, which is the Visiting Scholar Research Program. It's something TII supports. And my original project was on the umbrella topic of polynomial methods in combinatorics. So so this problem, one of a special case of this problem is actually an application of what I just said, using polynomial techniques to solve combinatorics problems. So we'll get to that. So let's start. 1 second. Right. So first we start with the definition. So is the second slide visible? Okay, yeah. So first we start with the definition. A Kakia needle set, or simply a Kakia set, is a subset of the coordinate plane of R2, inside which you can rotate a needle of length 1 completely around. So this definition was first introduced by Kakia in 1917. So it's a set in which you can turn a needle of length 1 completely around. So one of the most obvious examples is a circle of diameter 1. So as you can see, you can take the needle A dash and just rotate it around completely. So people tried to find some non-trivial examples, and then the first non-trivial example that people observed was the deltoid of area pi by 8. So as you can see, this is one example where you can again rotate a unit needle completely around. So one of the most natural questions people were interested in answering is what is the minimum area of the Kakia needle set? What is the smallest area you can achieve? And it was originally believed that the deltoid example that you just saw of area pi by 8 was the smallest possible Kakia set in terms of area. However, in 1928, Vesikovich proved that there exists Kakia needle sets in the plane having arbitrarily small area. So at the time that was a very important result, and it was very surprising. So now we look at the problem in higher dimensions. So for higher dimensions, the problem is slightly modified because now there's no notion of rotating as such, but we understand that it's equivalent to having, equivalent to the fact that you can orient the needle in any direction, that's equivalent to the n equals to 2 piece. So for n at least 2, a Kakia needle set in Rn is a set in which you can rotate a needle of length 1 point in any direction. So once again, people were interested in finding more about Kakia needle sets in Rn. Specifically, what can we say about their size? For some definition of size that we will talk about in a bit. So before that, I'll mention a more general idea which was found by Vesikovich, which he used to sort of solve the problem for n equals to 2. So a Vesikovich set is a set of points in R2 which contains a unit line segment in every direction. So it's a set which contains a unit line segment in every direction. So now what's special about this set is that every Kakia needle set must be a Vesikovich set, because you are rotating the needle through 360 degrees, so you must have a line segment in every direction. However, the catch is that you can actually have Vesikovich sets of area exactly equal to 0. So think about it, when you have a Kakia needle set, you need to rotate the needle around 360 degrees. So it's supposed to be a continuous motion. So although you can go arbitrarily close to 0, you can never actually get an area of 0. But Vesikovich sets actually can achieve area of exactly 0. And this is a theorem which was proven by Vesikovich in 1919, that there exists Vesikovich sets in R2 arbitrarily small area, or more precisely, dynamic measure. So this is probably a foreign concept for those who have done a bit of mental theory, but I hope you can understand the notion. So I'll just give an idea of what the Vesikovich construction was for arbitrarily small area Kappia sets or arbitrarily small area Vesikovich sets. So the construction was that you start with a Kappia set and you slice it up into a lot of pieces, and then you sort of place them close together and so that they overlap a lot, and then again you start slicing them. So towards the end you end up with a very spiky thing, like the last photo you can see, the left bottom photo, which has a lot of spikes. When you continue doing that, you end up having a lot more spikes and the area becomes very small. So this was sort of the construction very roughly which Vesikovich came up with. So now, moving on, we saw that Vesikovich sets in R2 can be very small in measure, but what can we say about them for other notions of dimension? So one of the more important notions of dimension for higher dimensions in R3 and above is the Minkowski dimension. So what is the Minkowski dimension? That's, for now you can just think of it as some notion of size. I will define it towards the end of my talk because it's otherwise not very important. You can think of it as like a notion of size. And this is a theorem proved in 1971 by Davies. Any Vesikovich or Kappia set in R2 has Minkowski dimension of 2. And this led to the more general conjecture in higher dimensions, which was the following. The Kappia conjecture, any Kappia set in Rn has Minkowski dimension of n. So this is what is called the Kappia conjecture, and this is one of the most notorious unsolved problems till date in geometric measure theory. And so now the main content of the talk is we will look at the Kappia set problem in a finite field setting. So till now we were concerned with Rn and so on, but now we will look at it in a finite field of the form FQN. So this is a field, so for those who are not very familiar with finite fields, you can think of this as an n-dimensional vector space over FQ, where FQ is simply the field 0, 1, 2 up till q minus 1, where q is, let's say, applied. See, that's one way of thinking about it. So this is our space of interest is FQN, and this time our lines are of the form x plus ty, where x and y are some fixed points in the set, and t varies from 0 to q minus 1. So t varies in FQ. And any direction in S is a class of y giving the same line. And also note that it is important to realize that in this setting, lines sort of overlap. So if you have a line starting here, then the other part of the line might go here. So I'll show you an example in the later slide that sort of clarifies this. We will see that a set S contains a line if it contains all q points on the line. Obviously there are 2 points. So now this brings us to definition of a Kappia set. A Kappia set in FQN is a set of points which contains a line in every direction. So for our definition of lines, a Kappia set is one that should contain a line in every direction. Pretty much similar to how we define it in Rn, how we define a Vesikovich set in Rn. So moving on. So these are some examples of Kappia sets in F3 and F2. So as you can see here, the lines sort of overlap. They sort of loop around of sorts, apart from the diagonal lines. So moving on. So again, people were interested in answering questions about size of Kappia set in finite fields. So this was first proposed in 1999. The question, what is the smallest possible size of a Kappia set in FQ? And this was posed by Wolf. And at the time, it was believed that this question was almost as hard as the original Kappia problem in Rn. But so first of all, there was some basic progress done by Wolf himself, which is the N-2 case. Any Kappia set in FQ2 contains at least q square over 2 points. So the proof is pretty simple. So how you do it is like the first line should contain 2 points, and then the second line must add q minus 1 point because they can intersect only 1 point. And then the third adds at least q minus 2 points, and so on and so on. And adding all of these, you get at least 2 times q plus 1 over 2 points, which is at least q square over 2 points. So this claim holds. So we should see that in FQ2, any Kappia set must contain at least q square over 2 points. So this led to what was called at the time the finite field Kappia conjecture. Any Kappia set in FQN contains at least Cn q to the n points, where Cn is a constant depending only on n. So this was the conjecture. So try to think about it for a while. It says that every Kakia set in Fqn contains at least some number, some constant times the number of elements in the field, number of points, but that constant only depends on the dimension. It does not depend on what time and what field we are working on. And this was initially believed to be as hard as the Kakia problem in RNA. However, this problem was resolved by Ziegler in 2008 using what is called the polynomial method in algebraic external combinatorics, which led to a very simple proof. This proof is pretty short and I can even present it to you in the next 10 minutes. So, the will prove that any Kakia set in Fqn contains at least n plus q minus 1 choose n, which is at least q power n by n factorial points. So, in this setting, you can take Cn equals 1 by n factorial and you are done. So before we move on to the proof, I present some lemmas. So the ideas involved in this proof are pretty simple and generalize the following well-known facts about the polynomials in one variable. So first of all, obviously we know that every polynomial in one variable of degree d has at most d zeros. I will call this the fact 1 from now on by referring to it in the proof. And also we know that for every subset e in Fq of size at most d, there is a non-zero polynomial of degree at most d that vanishes on it. So this is basically linear algebra of sorts, that if you have at most d points, then you can find a polynomial of at most degree d that vanishes on it. So moving on. So we will present two lemmas, which will be generalizations of these two. So first lemma is called the Schwarz-Zipper lemma. So what it says is that if you have a non-zero polynomial p of x in Fq x1 up till xn, so if you have an n-variable polynomial with coefficients in Fq p of x and it has total degree d, then it can have at most d times q to the n minus 1 roots in Fqn. So notice that this is of course obvious generalization of the fact 1 of sorts, because here you can just plug n equals to 1 and you get the previous fact. So the proof proceeds by induction of n, and the fact 1 as previously stated serves as a base case. And now for the inductive step, we split p of x into sums according to the powers of xn. So what I mean is I write p of x equals to g0 plus g1 xn plus g2 xn squared and so on until gn xn to the power l, where l is the degree of xn in p of x. And the gi are all n minus 1 variable polynomials with coefficients in Fq. So now what we will do is we will think of every element in Fqn as a comma b, where a is an element of Fqn minus 1 and b is an element of Fq, and we will try to understand how the roots work, how when can p of a comma b equals to 0. So now consider the roots a comma b such that gl of a equals to 0. So gl of a was the coefficient of x, xn to the power l, which is the highest degree coefficient. So by inductive hypothesis, because it's an n minus 1 degree polynomial of degree d minus n, you can have at most d minus n times q to the n minus 2 of them. So now think about it. For every such a, when you sort of fix a such that gl of a equals to 0 and you view it as a polynomial in xn, you understand that the leading coefficient is 0, which means that the entire polynomial must actually be 0. In other words, for whatever choice of b you take, you will have a root. So this gives you at most d minus n times q to the n minus 1 roots for p of x in Fqn. So this is one case. For the next case, we consider all those roots a comma b such that gl of a is not equal to 0. So now when you plug a into the in the first coordinate and just look at it as a polynomial in xn, you know that the polynomial is not 0. Right? But what does that mean? That when you now view it as a polynomial in xn, it has degree at most l, and its leading coefficient is not 0, so it's actually a non-zero polynomial, and hence it can have at most l roots, right? Because the degree of xn is l. So you can have at most n elements p such that p of a comma p equals to 0, and for every such element p, there are at most any choice of a works. So this gives us l times q to the n minus 1 such roots. And so adding up, you know that you have p minus l times q to the n minus 1 plus l times q to the n minus 1, which is d times q to the n minus 1 roots. So this was our first lemma that says that if you have an n-variable polynomial with coefficient Fq and degree at most d, then you can have at most d times q to the n minus 1 roots. So moving on, I will present the next lemma, which says that for every subset of E of Fqn with cardinality of E less than n plus d choose n, there is a non-zero polynomial p of x with n variables in n variables with coefficients in Fq of degree at most d that vanishes 1 p. So it basically says if you have a small enough stack, you can find a low degree polynomial that vanishes on it. So in some sense, it is a generalization of the second fact sort of sort. So how does the proof proceed? So first of all, we look at the vector space of polynomials in n variables with coefficients in Fq of degree at most p. We claim that this has dimension n plus d choose n. So we call this space VD. So how we prove this is pretty simple. Note that the basis is given by all elements of the form x1 power s1, x2 power s2, till xn power sn, such that total degree summation of all the SIs at most t and all the SIs are non-negative. And of course this is the basis. So how do you calculate the number of such tuples SI such that their summation is at most t and all of them are non-negative integral? There are many ways of doing this. One of the ways is like you can map this from s1 up till sn to s1 plus 1, s1 plus s2 plus 2, s1 plus s2 plus s3 plus 3, and so on until summation of all the SIs plus n. So note that this gives an n-size subset of 1 to up till n plus 2. And right, and of course this map is bijective, and thus the number of such sequences must be n plus t choose t. So we proved that the vector space of all polynomials and n variables of degree at most t is n plus t choose t. So now the idea is basically you have a size problem. So now the vector space of all functions from E to Fq has dimension E, which is obviously less than n plus t choose t. Why is this helpful? Because now you can just consider the evaluation map P of x, which maps to P of A belongs to E. And this is a linear map of vector spaces from VD to FQP, when U was the set we originally defined to be of small size. And since it is a map from higher dimension to lower dimension, I know that it must have a non-trivial kernel. Hence, my lemma stands to it. So you can find a polynomial of low enough degree that binds to the set. So equipped with this, we move on to the proof. So proof of the main theorem. Any Kazi set in Fqn contains at least n plus p minus 1 choose n points. So next, at least qp and by factorial bound is easy. It's simply some binomial coefficient manipulation, so I will avoid talking about that. So now, for the sake of contradiction, assume that there is some k with size less than this, some Kazi set such that it has size less than this. So now, since it has size less than this, I know by the vanishing lemma, which I just proved, that there exists some polynomial n variables with coefficients in Fq of degree at most t, which is at most p minus 1 that vanishes on k. What we will now do, here comes the trick. We will break p of x into its homogeneous components. What is a homogeneous polynomial? It is one such that all of its terms at the same degree. So pi of x has all terms of degree I, and so on. So now p of x vanishes from the non-empty set, so it is actually non-zero polynomial. This is actually pretty important. So now note that for every v in Fqn such that v is non-zero, there exists a w in Fqn such that the line w plus tv, where t carries over Fq, is contained in t. This is basically saying that the line with sort of slope v is contained in k. And hence we know that p of w plus tv equals to 0 for all t in Fq. That is because all of these points in the Kazi set, and p vanishes over the entirety of the Kazi set. So now we can think of p of w plus tv as a one variable polynomial in t, right? And I know that it has degree at most t, but I also know that it vanishes in all q points of Fq. Hence, it must be the zero polynomial in t because it vanishes on way too many points. But note that the coefficient of t power t in p of w plus tv is precisely pd of t. If you just expand it out, then you understand the coefficient, the highest coefficient of t power t in p of w plus tv is pd3. But since it's actually the zero polynomial, pd of 3 must be 0. But again, here's the catch. You know that v was arbitrarily defined, and also pd of 0 must be 0 because of homogeneity reasons, because all the terms have the same degree. Hence, we may conclude that pd vanishes on all of Fqn. So now, finally, we have a degree contradiction. This means that pd of x has q to the n roots, but by the Schwarzschild lemma, it can have at most d times q to the n minus 1 roots, which is strictly smaller than q power n, because d was strictly smaller than q. So, hence by the Schwarzschild lemma, we see that pd of x cannot be a non-zero polynomial. If it was, then you would run into a problem. Hence, pd of x must be the zero polynomial, which is a contradiction, because it says, initially we saw that my p of x should have been a non-zero polynomial, but its highest degree double zero. So yeah, that ends our proof. So yeah, so thanks for attending. That was all from my side. And for there is an addendum about Minkowski dimension. So this is sort of how you define it. This is might sound kind of unintuitive initially. I'll send you the slides. Maybe you can have a look. So any quick questions? Maybe if there's no 10-15 seconds, probably if anyone wants to. Okay, I guess not. So yes, that is all from my side. So I think I would like to welcome the next speaker. I think it's Vinayaka, who will be talking about automated theory and languages. So yeah, over to you guys.
Thank you.
Thank you.
आप जो लिख रहे हो उसका फोटो ले लूँ मैं?
Talking about automated theory and languages. So
Very loud.
So we're interested in formalizing what the notion of an algorithm is. So intuitively, if I give an input, an algorithm computes an output. So basically, it's a function from the set of our inputs to outputs, and algorithm is computing that function. So we want to ask for any given function, do I have an algorithm that computes that function? So basically, we want to find out the set of all computable functions. So now we'll consider a set membership problem, which is given any set S and a certain description of S and the element A. Can I decide using an algorithm whether A is an element of set S? And this is same as the problem of computing a function. If I look at the graph of a function, set membership problem for the graph is basically same as computing the function. So we'll go over some basic terms which I'll be using often. So alphabet sigma is basically any set of some finite set of symbols. And the symbols are irrelevant to what we're discussing right now. And we all know what a string over alphabet, given alphabet is. And sigma star I define to be set of all finite strings over sigma. So we now define formal languages. So formal languages is basically any subset of sigma star is a formal language. So an example of formal language would be a string which has even number of zeros and odd number of ones. And we're interested in set membership problem for formal languages. So we have different models of computation that we can use to formalize what an algorithm is, and we have some of them. We'll be going through a few of them now. So first one is DFA, or deterministic finite state automata. So formally, what a DFA is a tuple which contains a set of states, an alphabet over the input string, a transition function. The transition function has an input, or it takes in a given state, takes in the alphabet, and tells you what the next state will be. And we have a initial state and the set of exception states. I think an example will make things clear. So I want to draw a DFA for this particular language, which has even number of zeros and even number of ones. So this arrow represents my starting state, and if I have a double circle, that represents the final state. If after processing the string, the automata ends on one of these final states, then that string is part of my language. So it's easy to see that this automata accepts the language. Because if you have even number of zeros, I end up on this side, and if I have even number of ones, I end up on the top side. So this would be the state which accepts that language. So I have a few more examples. This is a DFA which accepts all strings having 0, 1, 1, 0 as a substring. Just keeping track of whether or not I have seen that particular substring. So I'll skip a few examples. Then I'll define something called regular language. A language is said to be regular if there is an automaton DFA which accepts that language. So I have a few examples here. But it turns out that these are not regular languages. For these languages, there is no DFA I could possibly come up with which accepts precisely these strings. And the
Can
proof
you
of
go over the DFA examples once more? Like, what do you mean by accepting a string?
so if, after, for example, here, if I have a particular string, let's say I have a string 110. So I start here. After 1, I end up back in the same state. Again, after 1, I end up back in the same state. And 0, I end here, which is not a final state. This is only final state. So 110 would not be part of the language except by the DFA. But anything having 0110 as a substring will end up here. This language precisely accepts only the strings with 0110 as a substring. So I will not go over the details of pumping lemma, but basically what pumping lemma does is captures the notions of loops in a DFA. So DFA is a finite machine. I have a finite set of states. So the language it accepts can be infinite precise. And it's only possible if I have loops in the DFA. So this is what it captures, and this is used for proving that certain languages are not regular, for example. And we'll come to another example of a model of computation. This is something called NFA. I think it's best understood by an example. So in a DFA, given a state and an alphabet, I have one unique state where it can go to. But that is not so in an NFA. So how you would imagine is, I start over here, and let's say I encounter the symbol 0 right now. So I could either stay in this state or go to the next state. So you imagine imagine standing there and creating a clone of yourself, sending one clone to the next state and one remains here. Let's say I encounter one. So one of the clones will come here and the other clone will go to this state. And let's say now I encounter 0. This clone has nowhere to go, so it essentially dies. But this clone finally reaches an acceptance state. So I can say that the NFA accepts a language if after a given string, even a single clone manages to survive and reach a final state. Then the language is said to be accepted by NFA. So this seems to have more computational power than a DFA, but it turns out that the class of languages accepted by NFA and DFA are precisely the same. That is, for any given NFA, I can construct a DFA which accepts the same set of strings. So now I'll come to something called regular expressions. So I have any expression, let's say in ordinary arithmetic, like 2 plus 3 minus 4 something, and it evaluates to a number. So regular expressions are just basically random symbols which evaluate to a language. And I'll give you the rules of how they evaluate certain languages. So these are how I build my regular expressions, like the inductive definition here. So this, all A in my alphabet, this is a regular expression, and I have 2 other regular expressions. I will tell you what they mean in the next slide. And if R1 R2 are regular expressions, so are these. Like I have not told you what any of these mean, but this is what they are. Now we'll come to what they represent. So the language evaluated by this regular expression is just the empty language. The language evaluated by this regular expression is just the language containing the empty string. So these play a role analogous to 0 and 1 in our visual numbers. And language evaluated by this regular expression is just the string with just a single string of just A. And I have the base case now, and I can inductively show for the remaining regular expressions. R1 plus R2 evaluates the union of languages. R1 R2 evaluates to the concatenation of the languages, which I will find here. And finally, I have the star, which is called the Creamy closure, and that is defined this way. So I can inductively define L to the power n plus 1 this way. And H star is the union of all such. So we know that several different regular expressions can denote the same language. Just a few examples here. So 0 star, 1, 0 star would evaluate to this language. Basically, star is the set of all strings over this particular symbol. And similarly, this is the set of all binary strings, 0 plus 1 star, and have 1 in between, and again a 0 plus 1 star. So this would evaluate to all strings which have at least one in them. Skip over examples. So just a few nice algebraic identities of the expressions. So finally, like this is one of the theorems of which says that the languages which regular expressions denote are precisely the languages which also DFAs evaluate. The regular expressions are basically the same as DFAs. There are certain other properties I will not go into them for time. So this is a theorem which in great detail like classifies all possible regular languages. So it does it in terms of an equivalence relation. So what this symbol is, you start from the starting state of the automata, and after evaluating a string x, the final state it lands to is what this function tells us. And if 2 strings land on the same state after being evaluated by the automata, then they are related, and this is equivalence relation.
This automata is deterministic now.
Yes. And DFAs and NFAs are identical, so that doesn't matter what you choose. So this is the Mahel-Herold theorem. For the sake of time, I will move ahead. So if I were actually to solve questions like given a particular string, is it part of the language or not? This is Mahel-Herold theorem helps us to come up with nice algorithms to convert between these and actually find out the answer. So next we come to something called context-free grammars. So what a grammar is basically certain rules to derive strings. So I'll just start off with an example. So I have these 2 rules. S is basically some random symbol which I call non-terminal. It can either derive the empty string or it can derive this string. So I can apply the rules in any order I want, and I can use that to generate strings. For example, I can start with S, apply rule 2, get this, apply rule 2 once again, rule 2 again, and finally rule 1. And I end up with these strings. So I can apply these rules in however I want, and I can end up with certain strings at the end. And the set of strings I end up after applying these rules is called the language generated by this grammar. So formally, this is what a grammar is. just a set of non-terminals and some production rules with the start symbol. So this particular type of grammar I'm considering is called context-free grammar because if you note here, I have S here, right? So the production rule doesn't depend on what lies to the left and right of S. So it doesn't matter in what order I apply these rules, I still get the same string. If I have more than one non-terminal, it doesn't matter what order in which I apply them. Therefore, they are called context-free grammars. You also have context-sensitive grammars where it depends on the neighborhood of S matters. And like Noam Chomsky has come up with a hierarchy of different things, divided into 4 Chomsky hierarchies. But we'll be considering only context-free grammars. So for any derivation, I can come up with a parse tree, which tells you how I have obtained that given word. And this is just useful for proving theorems and stuff about grammar. And it turns out all context-free languages, all regular languages are also context-free grammars. So I have a regular language, I can come up with a grammar which generates precisely that language. So I also have something lemmas for this, I will skip them. So now we have another model computation as push-down automata. This is basically just a DFA, but I also have a stack with me. So I can read the input string, I can also read the top element of the stack, and based on both of them, I can decide as to what the next state of the machine will be and what to do with the stack. So I'll just leave it at an intuitive picture of what a PDA is. And here also I can modify the definition to include non-determinism, just like the DFA is. So I have to describe the languages accepted by PDA, I can define it in 2 ways. One is, if it's just like the DFA, it ends at one of the accepting states. This is a possible way to accept languages. Another way I can accept languages after processing the string, if I end up with an empty stack. There are 2 ways in which I can accept strings, and it turns out both these notions are equivalent. If I have a PDA which accepts the language with empty stack, I can create another PDA which accepts it as final state. And this is like another kind of grand theorem. Like, the languages accepted by PDAs are precisely the context-free languages. So now we come to Turing machines. So Turing machine, again, like this machine over here behaves like similar to a DFA. But now I have a tape which can be moved in any direction. Basically what Turing machine does is it takes into account the current state, current symbol it is reading, and it decides what the next symbol will be, what to write, and it can also decide whether to move to the left or to the right. So this is a read and write head. It can change the symbol, it can move to the right, move to the left.
It can change the pre-existing symbol.
Sorry? It can change the existing symbol. It can change the symbol and then decide to move to the right or left or stay there. So I can describe the behavior of Turing machine using such spin tuples. Basically, present state, symbol it reads right now, state decides to go to, symbol it writes instead, and what it decides to do with the head, where it decides to go. So I just quickly tell you what, like formally what Turing machine is. I think this is the set of states, this is the alphabet on the tape, and this is the alphabet, this is the set of symbols Turing machine can write, the set of symbols which is there on the tape initially. And I have a special symbol called blank, which I have an infinite tape, and like wherever I do not have any symbol, I denote it to be blank. And I also have the criteria that blank is the only symbol which I allow to occur infinitely many times on the tape. I don't want any other symbol to occur infinitely many times. And similar to a DFA, I have a transition function, and I have a set of halting states. So in Turing machine, it is possible that I have, for a given transition diagram, Turing machine never halts. It gets into an infinite loop. It will never reach a halting state. That is possible in a Turing machine. It is kind of the central idea in some of the theorems. So we have something called recursive languages. Recursive language is a language. It's the language if there's a Turing machine which accepts the language and it halts on every input. So I have a special kind of Turing machine which halts on every input. I give you a decisive answer whether the string is part of the language or not. But it's not necessary, right? Like I can have a Turing machine which does not halt. So such languages are called recursively enumerable languages. So the Turing, let's say I want to decide whether a given string is part of this RE language. So let's say the Turing machine hasn't halted after a certain number of iterations. So I do not know if it will halt after some more iterations or if it will go on an infinite loop. So like, it's undecidable. But whether or not a string is part of this language is an undecidable problem. The Turing machine may never be. And this is a key idea in, might have heard of something called halting problem, which Turing came up with. So the problem is to come up with an algorithm to tell you whether given Turing machine will halt or not, basically. And it turns out that that algorithm is also undecidable, which means the Turing machine may never give you the answer in finite amount of time. You don't know when to stop. Maybe you have to wait for like 10 more iterations or like 200 more iterations. Or you don't know if it's going to stop eventually or if it's infinite. So now we come back to the original question. Given any set membership problem, can we write an algorithm to determine whether the element is part of a given set? The short answer is no, and this is intuitively this is because the Turing machine has a finite description. The Turing machine is a finite size, and the possible number of Turing machines I can come up with is a countable set. But the set membership problem, sigma star, is an uncountable set. So in short, it is not possible for me to come up with a Turing machine for every set membership problem. In fact, most set membership problems there is no algorithm for solving it. So you can look at some of the equivalent models. For example, I can have a Turing machine with multiple tips instead of single tip, or I can have a PDA with 2 stacks, or I can have a non-deterministic version of Turing machine, or I have something else called counter machine, which you might have seen in electronics, something similar to that. But it turns out all of them have the same computational capacity as what a Turing machine has. Finally, we'll look at something called universal Turing machine. So Turing machine has finite size, which means I can come up with a string, finite string, which describes a Turing machine entirely. So I want to construct a Turing machine which has 2 inputs basically. One input is a given Turing machine as a string, and then the actual input. So I want a Turing machine which first reads the first input string, decides that it wants to behave as a Turing machine, and then evaluate the remaining string as though it is the first the Turing machine we just saw. And this is possible to construct such a Turing machine, but turns out it's also undecidable. So I do not know if this will halt or not, but I can construct such a Turing machine. And finally, we come to the Church Turing thesis. So a lot of different mathematicians try to formalize what an algorithm is. So we saw one attempt by Turing machine. So like Turing machine, Turing basically said what can be executed on Turing machine is an algorithm. That's his notion of what an algorithm is. Similarly, you have other mathematicians like Church and Gödel. Church gave us something called lambda calculus, which is to do with logic, and Gödel has given another system called general recursive functions. And the grand theorem of computability, I guess, is that all these notions of an algorithm are exactly the same. If I have a construct a function using lambda calculus, I have a Turing machine that computes the function, and vice versa. So all these 3 notions are equivalent, and that is the central idea of what computability is. And I will stop here.
Any questions?
Yeah. So you said that the central idea is that the 3 notions of an algorithm are same. Is it known or is it?
It is known.
And who is it?
Church.
Okay.
I don't know about this, but these 2 are working by Church. There's another 4th one by Post, which I'm not aware of. That has also been shown to be equivalent.
And all of it is needed?
I'm not sure. I know that these 2 are.
You mentioned all recursive languages are context free or vice versa. Like, I mean, all the equivalences they were all equivalences.
So a class of languages handled by DFS smallest, and PDAs are a superset of that, and Turing machines are further one more superset.
Yeah, but like DFA, NFA, regular languages are the same.
Yes.
Okay, but context free languages are larger.
Are not. And the languages, recursive languages are even larger. Thank you.
Thank you. The next speaker is Karthik Durum with on critical modules of semi-simple real numbers.
So it's basically a representation theory of D algebras. The introduction, like we define the algebras and some special properties they have. Then we look at universal enveloping algebra. It's similar to group algebra when you're working with representation theory of groups. It's useful in representation theory in general. And we look at some interesting modules like the Verma module and Whittaker module and some other things, IISc modules. So this is the definition. It's just a vector space with a special product. It's called a bracket, and it has this property that x is 0, and it has a Jacob identity. You might find this familiar from the cross product. Cross product forms a Lie algebra on R3. For the rest of the talk, we'll assume the field to be C. You can think of the Jacob identity as replacement for associativity because this product is not associative, which is, it's not even commutative. But this makes it easier to work with. One important example is the set of matrices from any vector space to itself. If you take the matrices, you can think of the product bracket can be given by xy minus yx. It's denoted GLB. Therefore, Lie algebra because xy minus yx lies in G, and you can check that this satisfies the Jacob identity and x is 0. And then some more examples are, it's a special linear algebra. Just take the set of all matrices with trace 0. If you look back at the definition of the product, if you have xn minus trace 0, xy will also have trace 0, bracket xy. So it also forms a Lie algebra. And you have abelian Lie algebras. Just take any vector space and then define the bracket to be 0. Just define it to be 0, and it follows, it satisfies its previous properties. So it is a Lie algebra. It's not very useful in general, but it comes up again and again. Then you have upper triangular matrices. They form a Lie algebra. It's just a small computation to check that they're closed in the bracket. And then you have strictly upper triangular Lie algebra. These are very important when you're studying semi-simple Lie algebras. Now we'll define what a representation is. A representation is just a map from the algebra to the set of matrices to a vector space. Suppose you have a vector space and we have the matrices in the vector space. You have a map rho from G to NV. And this is not just any map, this is a Lie algebra homomorphism. What does that mean? It should satisfy the bracket. So if we have rho x comma y, this should go to x1 minus yx. So in essence, if you are turning into some vector, it should be x1 minus yx acting on that vector. And then one example of a representation is you can take the Lie algebra itself to be the vector space it's acting upon. And you can say if you have x acting on y from the Lie algebra, you can say the action is given by the bracket, and this is denoted by add x. And this is really important because what you can do is if you have a semi-simple, if you have diagonalizable add x, because it's a finite dimensional vector space, any endomorphism can be written as a matrix. So you can say add x is a matrix, and if you have add x is diagonalizable, then you can use over C every diagonalizable matrix. You have eigenvalues, and then you have the eigenvalue decomposition of G. And if you have many elements which are diagonalizable, you can look at them as a family and decompose the entire space using that. So there is such a family of matrices. It's called the Cartan subalgebra. Don't worry about the definition. What it is that it has diagonalizable elements, and you can simultaneously diagonalize all of them. So what you can do is look at the eigenvalue decomposition of the Lie algebra with respect to that. What you get is something like this. So G equals H is the Cartan subalgebra, and you have G alpha, where alpha is the eigenvalue. In general, when you think of eigenvalues are one-dimensional, but because you have many, it's a family of elements. For each H in H, and so this is the Cartan subalgebra, you have H dot X equals some, let's say K1, H1 dot X equals K1 dot X. This is eigenvalue for H1, H2 dot X equals K2 dot X, K2 times X. K1 and K2 are elements of the field. So what you can define, like you can do something like h1, sorry, h times x equals alpha times h of x, where alpha is a max from the Cartan subalgebra to C. This is basically the dual of h. So that's what I've written there. These are just generalizations of eigenvalues. And so these alpha, G alpha called root spaces. And alpha for which G alpha is non-zero is called are called roots. And what's the semi-simple Lie algebra? Semi-simple Lie algebras are like special class of Lie algebras where the representation theory of them is like quite nice. If you look at groups, you have this every reducible representation decomposes into irreducible decomposition. The same thing happens with semi-simple Lie algebras. It's called Bell theorem, but it's quite complicated to prove, so I won't go through it. And the root alpha for which G alpha is non-zero is called a root. This set is called a root system. In general, it's finite dimensional because if any of the G alpha is not finite dimensional, you have the G is finite, not finite dimensional. If you're working with finite dimensional Lie algebras, the root system is finite. It's a finite set. And they have a lot of nice properties because you know that if alpha is a root, minus alpha is a root, if alpha is a root, 2 alpha is not a root. And it has certain special subsets called simple roots and positive roots. Simple roots are kind of like a basis for the root system. And positive roots are, like if you assign, okay, I'll just write it down. If R is the root system, you have delta subset R and pi subset R. For all x in pi, gamma in pi, you can write gamma equals summation Ci alpha I delta. Where Ci are integers, positive integers. That's it. So every element in the positive system can be written as a positive linear combination of integer linear combination of simple roots. And the next thing is R is just the difference of positive roots and negative roots. So everything is either all positive or all negative. So what happens is you have this. This is for semi-simple algebras. It decomposes into Cartan subalgebra. All the positive roots, each of them is one-dimensional when you are dealing with semi-simple algebras. So this is the one-dimensional space, and you have the negative roots. And this is a very nice picture which forms, and you can play around with them. Another property of roots is that if you have something in one root space and the other root space, and you take the bracket of them, you just go to E1 plus E2. So if you have alpha in x in L alpha and y in G alpha and y in G beta, you have xy in G alpha plus beta. And yeah, this concludes like the introduction part of the algebras. That's not a complete introduction, but what is necessary for our modules. And then we go on to universal enveloping algebra. Universal enveloping algebra is a structure we make to make our life easier when studying representations. So suppose you have take any representation, a module V, and an element V in that, and you have elements like xv or yv, where x is in the Lie algebra, x is acting on V, and this is another element in the module. Or you could also have xyv. What you could do is, instead of thinking about the module, you want to think about the Lie algebra itself. So what you could do is just write this xv as formally. Just write it as something like this, but instead we just put a tensor product here. What this says is like apply y, then apply x. And implicitly if you apply it to v, this is an element in the module. This is just a formal notation to like capture the action of the Lie algebra on the module. But then we have a problem. What would happen to xy minus yx, and you act it on v? you know, when you act on V, this should be equal to like xy minus yx acting on V, but this is equal to x comma y because representation is a Lie algebra homomorphism and this should satisfy this. So what we do is we take all this and you quotient by this ideal. What's the ideal? You have xy minus yx minus x bracket y. So quotient the tensor algebra by this. What's the tensor algebra? It says the direct product of the set of unity, direct product G, direct product T squared and T cubed. It's just a set of all elements like this. x1 tensor, x2 tensor, xn, where this is an element in Tn. So you can imagine what the universal algebra looks like. It's just tensor. Any element in the universal enveloping algebra, in the tensor algebra is a linear combination of elements with strict vectors. Not even linear combination, just sums of elements with strict vectors. And then you quotient the tensor algebra by those relations to make it satisfy the representation. So one consequence is that we have this universal properties for universal properties for universal numeric algebra. Given any algebra A, if you have a map from G to A, it's not just any map, it's a Lie algebra homomorphism. How is A a Lie algebra? You just give the product xy minus yx as a bracket. This will extend to a map from UG to A. So, you know, G lives inside UG, so you kind of have to give other elements and imagine A. And this will give us, like, this is a unique extension of it. So what do you do with this? Instead of any algebra, let's take A to be the matrices of some vector space. Then this will become a representation. So what this says is, if you have a representation rho of G to V, like NV, you have a representation of UG to NV. And you can go the other way because G is included in UG. You can just take the restriction of rho prime say of UG, and then you could say that is a representation of G. So what this means is that UG and G have the same representation theory. If you want to study the representation of UG, like if you want to study the representation of a Lie algebra, you might as well study the representation of UG because UG is associative. You see, it's defined using the tensor algebra, right? And the tensor algebra is associative. It doesn't matter in what order you multiply things, but the bracket is not associative. So it's a simpler object in essence, and you could use tools which were developed for associative algebras. And then there is just a nice theorem for working with the universal enveloping algebra. If x1 to xn is the basis of G, then elements of this form is the basis of UG. Because UG is an and this helps in like coming up with some theories. And, it makes it useful to when you're working with modules. Now let's start with some modules. One of the
Can you again explain the basis?
yes. So you know the tensor algebra looks like this, right? You have x1, x2, xn, and linear combinations of that. But what this says is that the universal enveloping algebra, which is a quotient of the enveloping algebra, quotient of the tensor algebra, has a simpler basis. You don't even have to worry about the order in which x1 and xn are written. You fix the order and then you just raise them to powers. And this is a basis for UG. In general, finding a basis for an algebra is like algebra or a quotient of an algebra is not very easy. So this is a very nice theorem which is very handy to use.
No, I think the question was what do you mean the basis of an algebra?
Oh, an algebra is, you can think of an algebra as a vector space with a bilinear product. So it is a vector space and vector spaces are bases. And whenever I say algebra, just think of it as a vector space with a bilinear product, just some dot. Formally, you can think of it like that. And yeah. So we'll start with our first module. It's called the highest rate module. It's a cyclic module, which means it's generated by a single element. Let's say it's the node. And how we define this module is like this. Let's say we have all EIs. EIs are the posterior roads. If we go back earlier to the carbon decomposition, here we are working with semi-simple algebra again. So EIs are the posterior roads, FIs are the negative roads, and we have the carbon elements. These are diagonalizable elements when you're acting on the semi-simple algebra. In general, they will not be diagonalizable in their implementation. EI is 0, and HI V0 is some lambda HI V0. What this means is that HI is diagonalizable for all HI in the Cartesian algebra. And lambda is just a dual element. We will take any element in H2 upon X. So HI V0 is an eigenvalue, eigenvector for HI. And what about FIs? FIs can act whatever they like, but in general, because we have a basis for the universal algebra, any element in a higher state model can be written like this. Let's say this is the basis for F1 to Fn, H1 to Hn, E1 to En. We know this is the basis for the Lie algebra. So if you raise them to powers, that will become raise them to powers and take monomials of that kind. It is a basis for the enveloping algebra. And then we could just take a general element like F1 part K1, Fn part Kn, H1 part J1, Hn part Jn, and E1 to En part I1 to In, acting on V node. Any element in this is kind of a spanning set for our highest rate module. But because we said EIs are 0, we can just forget about these guys because here we take EIs to 0, and because HIs act as constants, we might as well forget about these guys. So any element can be spanned by elements of this form. Any element in the module can be spanned. So
We have 2 minutes here.
oh really? Okay. Yeah. Can be not equals 0. So this need not be like this is a spanning set. It need not be a basis because for some product it might take it. This is a for some product of this it might take it to 0. What does that mean? Suppose we have something like if this were free in essence, it would not be 0. But then the module would not be reducible because you would have. Let's just go to the next module. What? Oh yeah, why are higher set modules useful? Because we have this like every finite dimensional higher set module is irreducible, and we also have that every finite dimensional irreducible SL2 module is a higher state module. So in a sense, higher state modules like solve SL2, irreducible representations of SL2. And here you have Verma modules. Remember how I said some of these could be 0, and this is not a basis but a spanning set. Now if you let FIs act freely, in the sense that none of these are 0, and all of them form a unique element, that is the Verma module. That is just a Verma module. And you could, this is a very neat construction of the Verma module. You take C alpha, which is just the one-dimensional representation of, this is the complex number, and you apply these conditions to that, and then you append the universal enveloping algebra behind it. It's a kind of a free generation of this module, and this will be the Verma module, and every higher state module is a quotient of this type, is a quotient of these modules. So Verma module is like it encompasses all higher state modules.
Do you have any questions? Stop here.
These are the lectures, sir. I'll put the slides on the table.
I think the next speaker is Anish from 5th year.
So right, like every other number theory talk, will either start from Riemann zeta function or FFT. So today, fortunately, we'll go to FFT, or rather, unfortunately, we'll again come back to Riemann zeta function. But so this is the general outline of my talk. I'll be telling you about this Belling transforms and how it's related to this Bernoulli numbers, or rather, where do Bernoulli numbers come up in the proof of FFT. And then we'll also talk about this PID Banach spaces. Remove the Banach space, think of this PID spaces. Why is it Banach is a different method? I try to give you some illusion. Then we'll see more constructions and we'll prove some. So just a general. So okay, unlike other talks, I'll have to give my references before that. So most of my material will be from the Organised M2 course notes, the function PID, and secondary reference is also, so Pida's book, Elementary Theory of L Functions and Existence Series. It's not elementary, but okay. And so this is also an important reason, the first one, the Fontaine rings and theoretical functions. So whenever I say the Xinhua lectures, it means the first one, and I'll say Pida. Washington's book is for something that I have planned, but I don't think I have time. And I have no obligation to finish my slides, so just stop there. So right, so let's start with the Belling transform. So given any function f, which is C infinity, and such that all its derivatives also decay exponentially, like very fast, then you define this LFS to be, this is called the Belling transform. So whatever this function is, the result that we know is that this function converges to a holomorphic function. You can ignore whatever jargon is written here if you don't know what holomorphicity is. It converges to a holomorphic function and has an analytic continuation to the entire complexity. And the derivatives, or rather the L values at only the negative integers, gives you certain nice values. Okay. So this is a Belling transform, and let's see what a Bernoulli number is. So if you consider this function, t by a to a raised to power t minus 1, and look at its expansion around 0, then you, whatever coefficients you get, those are the Bernoulli numbers. First few Bernoulli numbers are this. So a priori they look very random, and they are random. But right. So anyway, so these are Bernoulli numbers. We'll see how they are related. The point is this. Now I want to relate this Belling transform and zeta function. So this is the relation. When zeta is just the Belling transform of this and by f I need this. So if you do the Belling transform of this t by e power t minus 1, what you get is this. And as a consequence, this is what you get once you apply the theorem, that the special values of zeta function at negative integers is this. Okay? So it's related to the Bernoulli. So rather, like, why study this abstractly? Right? So let's see. So this is a famous theorem of Kumar, and this theorem is extremely important in the proof of property. What it says is, if p does not divide the numerator of please take. I should not have said okay, so whenever p does not divide the numerator of this zeta values, and this zeta values will bn by n plus 1, right? Minus bn plus 1 by n, minus 1 plus 1. The point is that, so every Bernoulli number is also rational, and the numerator, so whatever the expression is. So whenever it doesn't divide it, it does not divide the class number of this number. So what are class numbers will be defined tomorrow. So maybe you can see more explicit to it. So just think of it as some special number attached to each number field, and it's a finite number that is also going to be seen. Okay. So whenever it doesn't divide, this happens, and so this is a crucial step in the proof. Right? The things that we need to know is that if p doesn't divide the class number, we call it a regular prime, and otherwise it's irregular. Okay. What we know is that there are infinitely many irregular primes, but it is not known whether there are infinitely many regular primes. Infinitude of regular primes is an open question. There is genuinely no progress, and I think if right, so forget you told me earlier, but the infinitude of this does imply f, capital F. Okay. Anyway, so and a crucial ingredient that goes into the proof of Kummer's theorem is Kummer's confidence, which is whenever you have this two integers which are in the same equivalence class modulo phi of e power k, which is the earlier question. Whenever that is true, then this equivalence mod k. So some kind of like answer. So to tackle the proof of this Kummer's confidence, we'll now go to our construction of p-adic. So now I'll define a p-adic Banach space. A p-adic Banach space is a vector space over Qp. So Qp is a field where, so basically when you look at R is just the completion. So basically attach all the limit points of Q to get R, right? With respect to whatever Euclidean model is. I think you guys have seen at least the model. So same way, if you complete with respect to a different metric, which is the p-adic metric, you get Qp, and so it's a field. The point is that a p-adic Banach space is a vector space over there, and also whatever this technical, and there's a lattice, and by lattice I mean a ZP module need not be free. So whoever understands it. So it's a ZP module, and which is separated and complete with respect to the p-adic. So whatever these two words mean is this. I'm not explaining it because nothing is required. And you have valuation, and the valuation is as expected. So you can think of like how many times p divides this number. And this has the standard property of valuation, which is that it's greater than or equal to. So it's greater than or equal to the minimum of the two components. Infinity what?
He's saying n belongs to capital N in infinity, the supreme.
Okay. It's a formal thing. I'd rather not. So, n doesn't have infinity. So infinity is simple. It's just instance. I don't know how to explain this. But n doesn't have infinity. Ignore that. Okay, suppose n doesn't have. Right. So okay, it has the standard properties of your valuations. So let's look at some examples of p-adic Banach spaces. Of course, Qp is a p-adic Banach space by definition. It has the Zp as the Zp module. And so ignore this, whoever doesn't know this. So if it's the completion of the algebraic closure of Qp, then it is this. Okay, so I think I should mention this because it's a nice that so Qp, right? So it's complete. Once you algebraically close this, you can basically solve all equations over Qp. There are solutions. But this is not complete now, so you have to complete it. So whatever this is. Okay. So if you have Cp, then the lattice is the ring of integers. Similarly, if you have this continuous functions which takes values in Zp and spits out values in Qp, this is also p-adic Banach space, where now the lattice is this. Right. And now let's look at some interesting properties of this when you're working with p-adic spaces.
In this example C, evaluation is always not negative.
Yeah, no, it cannot be. It's a finite it's a closed subgroup of finite numbers.
So this valuation CP is not the same as valuation CP as a field. Because that takes all action.
Yeah, I know this. Yeah, I don't think that. Or could be, yeah. Yeah, the structure of CP is not as obvious. So anyway, so if you look at this binomial coefficient, so formally we are defining this binomial coefficient, right? So whenever x is an integer, you know that this is an integer, right? You're just choosing endpoints from k matrix. But now, this xn is in ZP, and why is this true? Is that whenever you take an integer, a natural number here, this is an integer, or rather natural number, and because the natural numbers are dense in ZP, you can show that the entire thing is in ZP. So why do we come up with this binomial coefficient? Is because we have to define something called a Miller constant. So this is whatever capital notation, and the point is that this function is this and y is this. So the important point is always below, which says that any continuous functions on ZP which takes values in CP can actually be written as a linear combination of this Miller coefficients times the binomial. Right? So it's an element in. The key point is that any f such that is an element called over some power series element. Right. So yeah, it doesn't matter. And yeah, this this condition means that this goes to 0 PI, right? Because too many p's divide here. So right, so what's so special about this? About p-adic spaces? The nice thing about p-adic spaces is everything needs to be just, your functions will be locally constant. In the sense that in every neighborhood it's just a constant function or just a sum of constants. So it's just a sum of this. Right? So that's what we want to capture. So again, if you look at this f sub zx, this function, again evaluated in some integer, then you know it's an integer, then again it extends to entire of z, because again z is dense. And it has this property now. So priorly this was defined for integers, now you define it for all of zp, and this. And that is just it. Okay. But now if you had z to be a primitive pth root of unity, then this is true. I mean, it's trivial once you know what p-adic numbers are like. And whenever you have this, if you apply this, and because z is the root of unity, pth root of unity, z bar p is 1, so z bar p bar is 1. So this is true. And because of that, the identity function, the indicator function on this coset, which are the open subgroups in ZP, becomes this. So it's a nice thing.
What does primitive mean?
So primitive means that so this is a group, right? So this is a group, right? Okay, you don't know what it is. Okay. Basically, so this is a group. I can that if you okay. This is a group, in the sense that if you look at these numbers, right? If you look at this numbers, what basically p plus 1 is 1, p plus 2 is 2 plus 1. So this is a group. Right? So in the sense that if you add two numbers you're still in this side, every number has an inverse here as an identity. So it's a group number. So any generator of this z1 p process, that's an equivalent to. So right. The point is that okay, this is the indicator function. Why I said this is just in some sense kind of bookkeeping, because you use it intrinsically in some clues which I will not discuss. I am just telling you guys a story, and you guys will figure it out. Anyway, so an Amis transform of a measure mu on ZP, a measure mu on ZP as a formal definition. You don't need to move it. The point is that an Amis transform takes your measure mu and sends it to a function of this to this. So this is the Amis transform. Okay. The point is that this Amis transform is an this mapping is an isometric on the set of all continuous or other normal measures. So again, technical things you can just ignore. You can just remember for now that this is an isometric. Right. And certain properties of Amis transform or other certain things that we make sense of, like what does it mean to multiply by an Amis transform? Okay. Sorry, by a function, multiplying a function by a measure. Right? So if you multiply the multiplication of a measure with a function is seen to be this evaluation with respect to this measure. And if fx is x, then your Amis transform is this. And if this is a formal derivative. And if fx is this, then your Amis transform is this. And now you have some action of phi and psi. And this phi action is just multiplying with the same p and then taking it. And what it does to the Amis transform is that, so basically applying Amis transform to the measure is the same as applying the function to the Amis transform. It should not just be this, and you also have the action of this xi, which is just now divided. So it's in some sort of inverse relation that you would expect, and that is actually true. That this composition is an identity, and whatever this technical thing on ZP. So entire our measure was on ZP. We want to now restrict our measure to ZP cross, and whenever you restrict, this is exactly the measurement. Okay, and. Right, so the action of this xi, sorry, what psi or xi, whatever, and the action of this xi is actually very important. It, in some sense, tries to capture the action of Frobenius. Whoever knows what Frobenius is, and it's actually very handy when you talk about these Fontaine rings in PID costumes. Again, fancy words, nothing to care about. And convolution of measures is the same thing. Like, if you have two measures, the convolution product is.
4 minutes.
Right. So now, with all this details, we can come back. We can come and do the proof of Kuhn's calculus. So right. So for every a in ZP cross, there is the measure lambda a. So is that the Amis transform is this. True. The next condition is if you evaluate x power n at this measure lambda a, then it gives you this one. Okay? So this is now looking familiar with our Kuhn's calculus. And this is exactly this. Okay? And just using this, now this is basically x power n1 minus x2. X is to the power n1 minus x2 evaluated at lambda. So this is exactly the same. Okay, so now we have proved Kuhn's calculus, and the point is that Kuhn's calculus has been proved, but the key point is that we have been able to construct these measures which are element in some power series, right? And that allows you to describe this So now we can construct our PID. So what is the type of the character? Doesn't matter. So this x is this is a type of character, and the key point is that why is it a character? It's multiplicative, and the key point is that any invertible element in ZP can be written as, and this x you can see it in terms of either you define it in terms of omega x by omega x, or you can also look at in terms of this PID exponentials. Right. So the point is, if lambda is a measure and u is this element which is also a topological generator. Whoever doesn't know what a topological generator is. So if you have this u, then there exists a measure, okay, on ZT such that when you apply, when you do the evaluation at lambda x of each x, or rather of this form is the Amis transform. It's actually just the Amis transform. So you have a measure whose Amis transform gives you a certain t. And now we can define your PID zeta. A PID zeta function is not a function in itself, it's a measure which evaluates to certain values from you. So this is the measure, And the point is that this exactly. So once you evaluate it, you get some special. So it's a measure which evaluated a certain function. This is something. So this function, in some sense, picks out the p part of your of the Euler factor in zeta. Okay. So the zeta function is this. So in some sense, picks out the Euler factor. Okay.
2 minutes.
It's fine. Okay, I'll just say that. Right. Okay, I'll just make one comment and I'll finish it. So the point is that now you can realize each value of zeta function as being as evaluating a measure. So this gives you in some sense a family of measures which evaluates to give you special values of your algorithms. So this kind of techniques are useful to bring out the coefficients in your L series or things like that. Because we do know that in Dedekind zeta function, the residue at s equals 1, which is basically picking out the first term in the fluid that gives you the class. So those kind of things are applicable in this. So yeah, so basically this construction of these measures lets you find out special values of the coefficients or the L values. And those kind of works are seen in the recent work of Dasgupta-Darman for looking at the star conjecture, or Kamte, Dasgupta-Venture's work in stars, full generality and Blumer star conjecture by Samit Dasgupta. So those are the remedies. But yeah, anything else?
Any questions?
Yeah. So, what exactly did you do in your project?
Look, unfortunately, it's too technical for me to make any progress here. But rather, this was not even my project. My project is actually leaving outside, but this is more of a motivation of what comes in. Well, certain technical things which are. So basically, you want to find special values of your Eisenstein series or like whatever L values that you want. Right? So you want to extract some coefficients in your L series. So how do you do that? Is through this families of measures, which lets you once you evaluate it, you get the special values. So that was the idea. But of course, it's too technical for me to do it. So I went.
Thank you. The next speaker is Mohit Raju from Fifth.
Firstly, I'd like to thank the organizers for giving me the opportunity to talk in front of you all. And another thing I want to tell you, so this sort of presentation is based on my VSRP project with Professor Sabyasachi Mukherjee at IISc Mumbai. So it's a good opportunity for second years and third year students to apply to this program. Any case, so the talk is about complex dynamics. So there's like two important words. So one is complex and one is dynamics. So dynamics is sort of the study of what happens over time or how things evolve and so on, right? And what is the word complex? So complex comes from complex analysis and holomorphic functions and so on. Any case, so we slowly look at what these things are. Okay, so starting with what are the objects? So one has some subject of mathematics, one has. So in the subject of mathematics, you have objects and questions. So some objects. So what are the objects in complex dynamics? The first one is the holomorphic function. Well, if you don't know what an holomorphic function is, think of it as a polynomial. Right? A polynomial everyone knows, right? You learned it in high school. So that's a map from the complex plane to itself. So that's a holomorphic function. Now of course you can add dots and it's still a holomorphic function. Okay, so of course, so this is a function, so it has to be defined on some domain, right? Some domain to itself. So the domain is X, and this domain is actually what we want it to be is some sort of complex domain or a Riemann surface. So in any case, so we won't get into Riemann surfaces. The point to remember is
by Riemann surface, think of the complex plane. We've all seen the complex plane, or some sort of Riemann sphere. So let's see what the Riemann sphere is. So this Riemann sphere, well, you just take the complex numbers and add an infinity. So you just sort of take the complex numbers, sort of make it into a sphere by adding infinity, and that gives you a sphere. So wait, how exactly is the complex numbers present? When you take the sphere, remove infinity, and you stereographically project onto a plane. So that's sort of, this Riemann sphere is complex numbers with that extra point. So it's a nice object which we call a Riemann surface. Anyway, so these are like the maps and these are the domains. Do you have it? Okay, what are the questions? The question is, you take this holomorphic function or polynomial and you apply it iteratively. You keep applying it again and again. And the question is, sort of what happens under this iteration? So you're applying things again and again, what happens? So that's dynamics, right? How does things evolve and so on. So a more, like, a further question you can ask is, when you start with a point in this domain and you apply it, the point will sort of hop around, right? As you apply f. So you start with z, and then it goes to f of z, and then it goes to f of z, and so on. So the point hops around, in the domain. Now the question is, what is the, that's called the forward orbit, by the way. This set of all places it goes to. Now the question asks, what does the forward orbit look like? So what is the sort of evolution of these points? So it's like three answers or three possibilities. It's not exclusive, it's not complete list, but three, basic things it can do is periodic orbit. The first one is periodic orbit, which starts at a point, jumps somewhere and comes back. So it sort of hops between some finite set of points. It just circles around, right? So it just starts at one point, goes somewhere and comes back to it. So that's a periodic orbit. Sometimes you don't have periodic orbits, you have some convergence. It sort of just wanders around, but eventually it sort of goes and falls into a sink or whatever that is. So this goes and converges somewhere. The opposite scenario is divergence. So what is divergence exactly? So mathematically, it's sort of said that if you have a compact set, like say think of the complex plane, if you have a box, like a closed rectangle, this sequence will eventually leave that box and go far away from it. So like it eventually not belong to a box. Given you give me any box or a compact set, it will eventually go outside it. So it's sort of going away from it. That's dynamics. So it turns out more important than asking what the forward orbit of a point is, in complex dynamics, it's usually more interesting to ask what happens to a collection of points. Forget a point, just consider collections of points. So collections of points are open sets or neighborhoods, as we see in like UM 101 and 1. So the question is, you start with a point and look at all the points close to it. That's a neighborhood of points. And the question you ask is, what happens to this neighborhood as you apply f? So you start with some small collection of nearby points, then you apply f, it goes somewhere, and then it goes somewhere, and so on. So the question is, what happens to this, nz, f of nz, f of nz, and so on. Right. So a more concrete question is, you start with 2 points inside this collection. Now, if I apply f many times, that's f of n, will they still stay close together? That basically means, put in another way, if I start with a small open set, and if I keep applying f many times, will that open set become larger and larger, or will it stay small? That makes sense. So that's a question one can ask, and that actually motivates like 2 very important definitions in complex dynamics. So one is a Fatou set and Julius set. These are 2 mathematicians, very important. In any case, so what is the Fatou set? So Fatou set is the set of points. It's sort of this, where things are more deterministic or more like together, like the together set. So that is, it's a set of all points z, such that if you start with a small open set of that point, like some neighborhood of that point, it will not grow, it will sort of shrink actually. So it sort of, so that means if you start with some 2 points in the neighborhood, if you apply f many times, you still stay close to it. But on the other hand, you have the Fatou set, which is more of a chaotic set, right? It sort of expands and so on. So the point is, if you start with a point and a neighborhood, any neighborhood, like however small you start the neighborhood with, and you keep applying f many times, it sort of spreads, become larger and larger, and until it eventually sort of fills up the entire domain, except one or two. Right? To summarize, for 2 is like, sort of where things become closer to each other. Julia set is where things go far. So these are 2 important definitions. Okay, so we have seen some complex dynamics, but it's good to start with some basic examples. So there's like z goes to 2 set, just multiplication by 2. Now the point is, so clearly 0 and infinity is something on a fixed point, right? It stays where it is. You apply, multiply this by 2, you get back the same. Now, okay, what happens to the other points? So this is our domain again, Riemann here. So you start with some point here. You keep multiplying by 2, it sort of goes closer and closer to infinity, right? So you start with the point, say 1, then it goes to 2 and then 4 and then 8 and to infinity. The point is, you start with any point away from 0, it sort of goes towards infinity, right? Except the 0. 0 just stays there. So the point, if you remove 0 over here, this entire thing sort of goes closer and closer to infinity. Yeah, sure. There's if people you know it, this is the 1-point compactification of the complexity. But it has more structure than just topology. Anyways, so that's right. So this is in some sense, the infinity point is an attracting fixed point. It's sort of attracting, and 0 is a repelling point. Now recall I defined this Fatu Julia set. Now the point is the Fatu set, which is sort of the getting closer set, is everything but 0. Because the point is, you start some set here, it will all sort of end up at infinity. So the Fatu set is everything but 0. And the Julia set on the other end is only 0. The point is, like, if I start with any small neighborhood of 0 and apply f, it will only become bigger and bigger, right? Small as epsilon dot, it becomes 2 epsilon, 4 epsilon, and eventually it's like a million.
Fatu set is just defined with respect to some point.
Not quite, it's the set of all points which behave that way, right? So it's a set of all points z such that any neighborhood mz of that point spreads out. So 0, then you pick any neighborhood of 0, it's sort of expands. It's a slightly convoluted definition, so it's a very simplified version and so on. But anyway, so that's like the 2 main objects one comes across in like complex dynamics. And the other sort of, we came across fixed points, so now we slowly go towards fixed points and end it all. So fixed points is like, of course, they're fixed. You apply f, you get f. I mean, you apply f. Yeah. Now, another interesting thing, we can differentiate these functions. Polynomials you can differentiate. So if you differentiate it, look at its derivative. It's either less than 1, bigger than 1, right? I mean, one of those 2 situations can happen. The point is, if it's less than 1, then it's sort of attracting. It's like sort of distances are coming closer to each other, right? So that means it's an attracting fixed point, clearly. But on the other hand, if it's like greater than 1, at least locally near to that point, derivative only captures local information, right? So at least locally near that point, it's locally repelling, right? So it's at least, okay, it's a locally repelling fixed point. That's it. But the point is, in the first part, because it's attracting, we can say it's in the Fatu set, right? Because you start at 2 points, you get 2. Now, on the converse side, can I say that if the derivative is greater than 1, can I say it's in the Julia set? Now, the point to remember is, the way we define Julia set, you start with any small neighborhood, it should eventually expand and become the entire domain. But here we only know that it's locally repelling, like it locally gets bigger, but what if you start with smaller neighborhood, it becomes big, but then it stops growing. That is a possibility, right? But it turns out, if locally it is expanding, it will never stop expanding. It will become bigger and bigger until it fills up the whole. So that's a theorem you can say. The point is, if there's a fixed point and the derivative is strictly bigger than 1, then it's locally expanding, but more is true. That is, any neighborhood, you start with any tiny bit of points close by, and you sort of consider this union of sorts, like this union of where these points end up in, like apply F many times and see where all that points go. It turns out this is the notation for Riemann sphere, the sphere I was talking about. It's the Riemann sphere, except maybe one or two exceptional points. There might be always some exceptions, but other than that, it fills up the whole thing. It spreads and becomes very, very large. So this is a very, to prove it, uses something called the uniformization theorem, which is again a big theorem in complex analysis, and it's difficult to prove. At least the only proof I know of involves solving a PDE. And if you should know anything about PDEs, it's that PDEs are very, very difficult to solve. So anyway, so that's a digression, but okay, I'll end the sort of talk with some small question. So you start with two maps, like polynomials, z over 2, z over 2, and this has some higher order term. Now in time and time again in MVC class, we learn, what do we learn? You can always forget about the higher order term. That's what we learn in MVC. The question is, does the similar thing happen in complex dynamics? Can I forget about the higher order term? So more precisely, I'm trying to ask, are the dynamics, the complex dynamics of f and g the same near 0? That's what I'm trying to ask. So more precisely, I've stated things here. Does adding higher order terms affect the dynamics? But also to ask this question, we need a further question. When are two dynamics considered to be the same? What is the notion of isomorphic for complex dynamics? Okay, before answering that, I might not answer it, but before answering that, forget everything, just come to another digression. So this is some interesting phenomenon, okay? So you start with a map Z goes to 0. Okay? So this is think of this as a complex plane. So far so good. So start with this circle. This is a nice little circle of radius 2. And then you apply this map Z over 2. What happens to the circle? It becomes a circle of radius 1. Apply it again, it becomes half and so on. So we get this concentric circles all going to 0. Okay, now let's look at the annulus or the ring in between the circles. Right? The point is, even this rings in between the circle all sort of fold into itself, right? So this ring over here, when you apply F, that is do Z over 2, it will become, like it will go inside, right? Z over 2, you just contract the ring by 2, it will fold up in some way. Okay, so this happens for the map Z over 2. Now come back to the question I was sort of thinking about. So come back to this Z over 2 plus some higher order term. Now the question I can ask is, for this map, can we find locally can we find a system of closed curves and annuli rings that map this rings sort of folding up nature? So the point is, there is some phenomenon happening here, right? Some folding up, some concentric rings. The question is, can I find the same for this map G? So can I find some, maybe not circles, but some curves, closed curves, and some space in between that sort of folds up and so on? Now, I mean, if these two things are equivalent in any sense, like whatever sense we define, they, like this answer to this question better be yes, right? Like, in some sense, I'm trying to say, if f and g are the same dynamics, then even for g, we should better hope to find something like this. So okay, I've asked so many questions, and I think I'm probably running out of time. So I'll just say the truth of what these things are. So the point is, the answer to question 5 is yes. Now a priori it might look almost impossible how you are going to find these circles, but there is methods to find them. So the point is, question to answer 5 is yes. This answer is correct. And sort of working backwards, now I will answer the question of what is equivalence of dynamics. So to motivate this, think of two matrices. When are two matrices the same linear transformation? Two matrices are the same linear transformation if they are like change of basis equivalent. Right? If you can change basis and get the same, get the other matrix, then they're equivalent. So that means they're conjugate to each other, right? There's some, if you've seen some linear algebra, if there is a change of basis matrix that you can conjugate with, then the two matrices are said to be equivalent or similar. That means it represents the same linear transformation. So similarly for complex dynamics, one can use the same definition. If you've given me f and g, we say f and g are the same, that is, the specific term is bijective, holomorphically equivalent, if there is, this bijective holomorphic map, this sort of phi, this change of basis, or change of coordinates if you're a physics person, or whatever. So some change of perspective, this bijective holomorphic maps, which conjugates the thing. So essentially, whatever is happening upstairs can be conjugated to what is happening downstairs. So that is the notion of equivalence we want. So to the question I initially raised about this higher order term business, so I have z over 2 and this higher order term. The question is, if I have z over 2 here and this z over 2 plus higher order term, can I find this sort of change of basis or whatever you want to call it? Right? So that's what. So I have z over 2, this thing, can I find some? So that's what we have ultimately boiled down to. So how many minutes?
Over time.
Huh?
Over time.
Okay. Yeah. And stop. I mean, interested people can ask me later. Let's stop. Huh? 2 minutes? Okay, I'll try to wrap this up in 2 minutes. So fine. Because let me see my own. Yeah, probably. Oh, that's 1 minute. So point is, see, we have this. So this is the diagram we want to achieve, right? We want to construct a map phi. Okay, we don't know how to construct a map mean, but we are mathematicians. We work backwards. Assume there's a map phi and then see what happens. So you just start with assume this diagram mode. So there is some God-given map that phi happens. Now you can, doing some normalization, you can assume 0 and 1. So the 0 maps to 0, of course fixed point better go to fixed point. And some derivative normalization. So assume this. Okay, you have one diagram, this happens. I mean, if you have one, might as well have two. And once you have two, apply induction, might as well have a chain of diagrams. Now once you have a chain of diagrams, okay, we have something here, let's see what's happening. So you start with a point here. So instead of going downstairs, let me take the weird way out. Let me take the mathematician way out. So I start with z, and I go to g power n there. Okay. And then, I mean, again, I don't know phi here. But the point is, what's the point? The point is G is a locally attracting fixed point. I mean, as locally attracting behavior. So the point is G power nz for large n is close to 0. But close to 0, we know something. 0 maps to 0 and identity. So some Taylor expansion business, I can approximate with itself. So even without knowing phi, I can approximate phi. So to see what's happening there. Because phi maps 0 to 0 and derivative is 1, you can approximate with itself and then go all the way back here. So that's sort of like, okay, this map was z over 2, so you do 2 times z. So 2 times z n times is 2 power n. So without knowing phi at all, just by assuming a God-given phi, we have some candidate of answer, right? The point is, so we can put phi equals to this limit. Now this limit, there is no phi here, so it makes sense, it's defined. So you just put phi inside that, take the limit, and then do some analysis and thank you.
Any questions? Can you share that
Sorry? Yeah. So length. Forget length. So when you see topology, you just forget about length. See, the point is, it's okay. Let us work backwards. You start with a sphere and call that the Riemann sphere. Is that okay? And then the way it's related to the complex plane is you stereographically project it, it becomes a plane, right? And call that a
If
complex.
you open the sphere and then make a hole at the top of the wall and then open it on the
Yeah, put a light at infinity and
Yeah.
Think of it that you are just quite literally pinch a hole and then pull out. It's an entire surface. And topologically, like if you don't have poles, it's the same. Like a ball is same to what, like something without, like this duster. If you use it.
Anyway, forget about distance. Distance we do not care
Because
about
we can
distance.
stretch out as much as you want.
So the point of topology is distances don't matter. We forget distances, angles, and anyway.
Can you please explain the forward orbit again?
Where?
Briefly.
So this one? So the forward orbit is just defined to be a sequence. So we have seen sequences in 101, right? Like it's sequence is just like collection of points. So this is a collection of points. The first point is Z. The second point is f of z. The third point is f of z. Fourth point is f of z. So that's a sequence of points, right? Like,
What do you mean by hopping around? You see, like periodic hopping around.
We can have those questions a bit later.
yeah, sorry, my bad.
So according to the schedule, the next speaker would be Samasya, but instead of him, Anwar is giving a talk on group theory.
So hopping around, it just means that you're applying the function. So you have some. So once you apply the function, you're in some part of the plane. Once you apply again, you might be in some other part of the plane. So that is what he means by hopping. For example, if you had f of x equals say 2x, just for real numbers, if you put 1, you're at 2. If you put 2, you're at 4. So you're hopping around from 2 to 4. That's what he means. It's an informal term of 4.
It's not math, it's just English.
Also, your definition of divergent wasn't the same as like not convergent, right?
No, sorry.
Good.
So my project was on finite group theory, but given the time restrictions, I've decided to tell you about P groups and proof of Silo theorems by some group actions and some study of P groups we can do via Silo groups. So I assume you know some group theory. It won't be too much basic things like Lagrange theorem and stuff. So by definition, P group is some group which has order. See, this is finite group theory, so I would not consider anything related to infinite groups. So finite P groups are those which have cardinality of some power of P. So basically mod G is P raised to alpha. Then Silo P subgroups of some group G, say G is P times alpha raised to n. So alpha is the highest power we can get out of P. So Silo P subgroup of G would be some subgroup of G that has order P raised to alpha. Maximum size that a P group can have in G. So what we show is this subgroup exists. There are three parts in Silo theorem. So one, we would show that this subgroup exists. H exists. Secondly, show that any two of these are conjugate in G. Second, if there are two such subgroups which have this order, then they are conjugate in G. Then say S and T are some subgroups, so then S is G P T inverse. And then we show that the number of subgroups that have this cardinality, the number of Silo P subgroups in a group, call that cardinality NP. So if NP is number of Silo P subgroups, then NP is congruent to 1 mod P. In fact, something stronger is true. If you replace P by this quantity, yes, where S and T are any two Silo subgroups of G, then you can replace P by this and this would still be true. So instead of doing the regular large group action proof of this first thing, I would take some shortcut So we to show this first theorem, we observe the lemma that this combinatorial coefficient is congruent to m mod p. Throughout the m is the same, that p alpha m is cardinality of G. So for proving this, we consider consider the polynomial 1 plus x raised to p, and observe that this is 1 plus x raised to p mod p, and what I do is if I apply p square here, then I multiply this again by 1 plus x. And then I write this as this, and then I write this again as 1 plus x raised to p square. You get what I do. So using this again and again, I can show that 1 plus x, I can show this 1 plus x raised to p to the m is congruent to 1 plus x raised to p to the m mod p. And get this in the game. I just iterated this, and now you can take power m on both sides. So this would be p alpha times m, and this would be this. So comparing coefficient on both sides, you get that. So this lemma. Define this to be set of all subsets of G that have cardinality p raised to alpha. So I would show that one of them is a group. So this is set X.
How do you know it's not?
Huh?
How do you know it's not?
No, it's just a subset. G has cardinality p raised to alpha times n, right? So I can just choose p alpha elements.
You're not saying it's a subgroup.
Yeah, I'm not saying
it's just a set of.
Yeah, it's just a set. Now what I do is see Gx on this set by right multiplication. I take any x and replace rectifying the multiplication as x times g, simply multiplying all elements of x by g. So the set xg x. So this is the group action I define. Since this is a group action, it partitions this into orbits, and I think it's called class equation, but basically it's partitioned into orbits because group actions are transitive. So this can be written as see what's the cardinality of this? This cardinality is this, right? Because I am choosing p raised to alpha elements out of a number of elements, and this m is not congruent to 0 mod p, so p does not divide. So total number of elements in this set is not divisible by p, so this is not congruent to 0 mod p. So there must be some orbit that has a number of sets that has cardinality not congruent to 0 mod p. So there is some orbit O such that p does not divide cardinality of O. So suppose n subset x belongs to this orbit, then by orbit stabilizer theorem I can write that mod of O is mod of G times divided by mod of stabilizer of x. And that implies that since p does not divide O, but p raised to alpha divides this, so p raised to alpha must also divide this. So this implies one result, p raised to alpha divides stabilizer of x.
What is stabilizer of x?
Stabilizer of x is those elements in G that fix x. So if you multiply all elements of x on the right by G, then you get the same set back.
You have half your time left.
No, I think the stabilizer of x is a pointwise fixing, not just.
Not 0.56. Fix is the set x, which has p raised to alpha elements. I call this is a subgroup of G. I call this H. This is one result, and what we do next is just take this definition. Suppose see if x, I saw that if I multiply all elements by x, then the cardinality of the subgroup would not change, and if x is in x and as h stabilizes x, then x times any element should also be a part of x, right? And hence this would always be a part of x, and hence this is less than mod x. But mod x is p raised to alpha, so mod x is less than p alpha, and p alpha divides mod x, hence mod h is equal to p raised to alpha. So I have constructed a subgroup of G that has this order p raised to alpha.
I think it has to be set. It's not set fixing because this formula doesn't work for set fixing. It has to be the specific element fixing. It has to be pointwise fixing for this orbit stabilizer theorem.
The point, the thing on which the group is acting is the set of sets, right? So it fixes the set.
You're saying
I define this to be the family of sets of size this. So if the stabilizer fixes the set in
you're saying x is an element of omega, it's a stabilizer
yes.
of
And so if x is any element in capital X, then x has to belong in it because this h stabilizes this. So I constructed this. This also directly implies Cauchy's theorem. See, I constructed a group with order p raised to alpha. So I consider any non-identity element in this. Suppose x is not equal to identity. Then order of x has to divide p raised to alpha. That implies order of x is something p times something. That this m can be divisible. It's a power of p, then I can extract p out. And then I see that order of x raised to m is equal to p. Hence, every group, if p divides to g, then there is an element of order p. See, I cannot go through proofs of all these, so I would just state you some interesting results that I have proved in this. So of course I told you that two zero subgroups are conjugate. There is an interesting use of the conjugate part. So suppose n is any normal subgroup in G and say P is some zero subgroup. P is some zero subgroup. Then we claim that G can be written as n. This this is we show that conjugate of P by any element of G belongs to given any subgroup n, I define P as 0 P of CELO subgroup in N, then it follows that any conjugate of P is a subgroup of any conjugate of N, but since N is normal, this is equal to N. So now applying that any conjugate of CELO subgroup is also conjugate, I can take any element N, so conjugated by Gn of P would also be CELO subgroup of N, and I can vary N over N, and hence some conjugate of this must be equal to P, as P was also a CELO subgroup of N. And this directly implies that Gn is an element of Gn is an element of Ng of P, because Gn conjugates P to itself, and taking and this side I get G is an element of this, and hence for all G I can write G as this. So this argument and its variants are used
you are over time.
Can I state 2, 3 more results? I would just state the results now. So see, there is see, if you take the intersection of all CELO subgroups, it's denoted as OP of G. There is a theorem that see, if there is a theorem that states that this intersection can be achieved only by two CELO subgroups. You need not take the intersection of all CELO subgroups. And given the NP-G is congruent to 1 mod P, we can prove some interesting stuff. So using this, we can show that groups of order P raised to alpha times Q are not simple. Stuff like groups of order P square, Q square are not simple. We do this by, if we assume it's simple, then both of them have to be 1. Then we derive contradictions in congruence and stuff like that.
The next speaker is Samasya from the 3rd year.
Good afternoon, everyone. I am IISc. I'm 3rd year mathematics teacher. I did my summer project under Dr. Google Copy of Computer Science Department. My research interests are probability and stochastic optimization. Basically, this is an application of probability. This discusses convergence rates of interesting problem that I will show you. So in this presentation, we discuss the convergence rate of this problem. We have a measurement model y equals ax, where A is a matrix and x and y are random variables, which are random vectors, and A is a known tall matrix. A tall matrix means that we have more rows than columns. So we sample y at each discrete time and attempt to find an estimated value for x, which is also random. So we devise an online algorithm for this. The difference between an online algorithm and offline algorithm is that if you've done any DSA, you would know that there is something called selection sort and insertion sort. So selection sort, when you, for example, if you want to sort from say minimum to maximum, you choose the whole list has to be given to you. Then you choose the least element, put it, then take the element away from the main list, then go for the next shortest, next smallest element, and so on. Basically, you need the entire list, entire input in all of your computations. When in an online algorithm, you need step by step. For example, insertion sort, you will just discuss one of the elements and not try to find the minimum or maximum over an entire input set. So here we will just discuss. Here we will be discussing an online algorithm which just needs that particular data point that we require. So as I said, x is basically it's a d-dimensional random variable. It has finite mean and covariance entries. So in the multiplication of y equals ax, we do not directly perform the multiplication of ax. There are agents that do this for us. There are 3 such agents. So the ith agent has access to the random variable ai times x. Basically, ai is the ith column of a. So basically, you take the transposition of that column and multiply it with x. So you have access to just that random variable. The interesting part is, however, there are out of the p agents, there are a few agents. It's not a lot of agents. There are a few agents that do not yield the right multiplication. They may give you any real number. From minus infinity to plus infinity, they'll give you any real number. You do not have control over what the number that malicious or adversarial agent gives you. So basically, at each discrete time, we pick one of these uniformly as your agent, in, then compute the value of y of in. Now, in will give you the right sample if it's non-adversarial. If it's not part of m, it will give you the right multiplication theorem. And if it is indeed an adversarial node, it will give you any real number. You do not have control over what you get. Either way, for a sequence of in, you obtain a sequence of yn of in. Basically, the goal is to develop an online algorithm that is just taking one sample by sample and not the entire samples together. So basically, you cannot take 1 million data points and put it into the algorithm and expect it to give you an answer. It's too much of data for it to computationally be viable. So we devise a online algorithm to estimate mu. Basically, we don't even know whether this converges or not. We prove that we show that this converges almost surely. If you understand the term, it's fine. Even if you don't, just consider that it converges. We show that this converges, and we also determine the rate of convergence. So the approach is a typical stochastic gradient descent on, this is our objective function. If you've done any gradient descent before, you would know what this means. So this is just the L1 norm of this. We can choose to start with any x0 or y0. Preferably not, if you knew the value of mu, preferably not for mu. But again, there's a very low chance you would know the value of mu. Now this is the algorithm. So all of these are defined, like some of these are defined already. This is just the segment function. Basically, this is the direction of that difference of yn minus that particular column that you choose. And this is similarly an incrementation on yn. You increment both on this. A and bn are the respective step sizes. And ui is the ith column. The algorithm is not very important for our talk. It is important in general to deal with the proofs, but I just give an overview of it. So we cannot just prove any alpha and beta n. We have a few assumptions on them. We need to have them monotonically decreasing for starters. Then there should be square sum of them. That is sigma, the sum of alpha n square from n equals 1 to infinity, and the sum of beta n square from n equals 1 to infinity. Both of them are finite. But the sum of alpha n's and sum of beta n's are not finite themselves. The square sums are finite. So we could choose a typical example of these. Like in general, when you discuss any ML algorithm, you choose the step sizes to be some powers of n for easier computation. We could choose alpha n equals n power minus n, similar for beta n. We have a few constraints on A, and once you decide A, you could decide B. On simulations, we took the average of these two to be our mean, so it made it easier for us. This is an example. So, yeah, now you have, for example, for this A, this is just a geometric median problem. So there are 5 of the same numbers. If you have 2 adversarial nodes, you see that it converges, but 3 does not make it converge. Similarly, in this matrix, you have 1 adversarial node that converges, but if you make 2, it won't. Basically, you cannot have too many adversarial nodes, but you can have up to a certain extent, which is also computationally already decided. So yeah, I'll just describe briefly the Sood strategy. Here's the algorithm again.
So yn is a function, like yn of in plus 1 in the algorithm.
It's a sequence.
If you can show the algorithm.
Oh.
Yeah, so you are saying the yn plus 1 of in plus 1. So is that a function with input in plus 1?
So basically this is, I've discussed this already, right? This is AI and the transpose times this value. Basically the transpose, I'll show you. So I'm looking at this basically. This transpose times this, etc. By this I mean like it's n, not n plus 1. This is the sequence we are looking at. This is what you get from the computation. Yes.
Why do you need an adversary in your model?
In your model?
Yeah, I mean, why are you saying there are non-zero adversaries?
What is the motivation for adversaries? There are problems that have been discussed in the references which I will show you that require adversaries. That happen to happen. So in this algorithm, note that there is no Xn. There is no involvement of Xn's iterates in Yn derivative. Of course, like the decision of Yn and Xn happen parallelly, but in a direct sense, there is no Xn here. And of course, so now M is basically a set of adversarial nodes. So MC is the set of non-adversarial nodes. So if you have non-adversarial nodes, it is intuitive to expect that this would directly go to 0. This is so basically the norm under MC. This is the non-adversarial node. Norm under that is basically the sum of this square, with the root of the sum of squares of all of these terms. Yn of I minus E of Y of I. So now we can split this algorithm into two. We can analyze the algorithm in 2 parts. We perform a this is called a 2 time scale analysis. So the assumption is that Bn goes faster to 0 than An goes faster to 0 than Bn. So if An goes faster to 0, that means your changes in Xn eventually will be very small. Yn's changes will still be significant when compared to those of Xn. So we can break the analysis into 2 parts. We first analyze Yn. Since it doesn't need the support of Xn, we first analyze Yn. We set Xn to be some arbitrary sequence beginning with x0.
Now, as we studied in ODE, this is a asymptotically stable equilibrium for this ODE that we have devised here. So once you have that, it is clear that this goes to 0. If you have this to be the asymptotically stable equilibrium. Since it's unique, we can state that this goes to 0. It's a standard result. Now for Xn's analysis, now I'll go back. So basically we have stated that Xn's changes are very small when compared to Yn. So in Xn's perspective, Yn is already converged. So we can put Yn equals this. So we do not go into more detail regarding the analysis of Xn. So we do it using a differential inclusion analysis. If I had more time, I would explain the analysis. I will go into convergence rates. So basically, the previous paper proved that Xn's iterates converge almost surely. In the rest of the presentation, we will look at the convergence rate of the algorithm that I discussed. So this is the definition for a convex function. Of course, this is the definition for a strongly convex function. Basically, this term is extra. Lambda is called the parameter. I could have written just lambda here, but this is strongly convex with parameter lambda. So it is not difficult. If this is our objective function, it is not difficult to show that this is convex, but not strongly convex. Now we look at the convergence rates of the average. We could have very well looked at the, this is supposed to be I. We could have very well looked at the convergence rates of just the iterates, but the average converges faster than just the iterates. So we are looking at the average. Now this is reference to, I have attached the references. That reference shows that in the non-strongly convex stochastic gradient descent, for alpha of the form n power minus a, the convergence rates are big O of n power a minus 1. For example, if you choose say 0.8, n power minus 0.8, so you get n power minus 0.2 as your convergence rate. So basically the best, since this model is anyway going to be worse than this model does not discuss adversaries. This discusses a case without adversaries. So our model is anyway going to be worse than this. So the maximum possible convergence rate is this. We go of 1 by root n. So the conjecture is the same convergence rate holds in our case also. Basically, this is interesting because we would expect this to be slower than the case without adversaries, but that is actually not the case. We still have the same convergence rate. This is a very strong result. We have proved it in the case of a, basically n power, for alpha n of the form n power minus a, we have proved it in the case of a from 2 by 3 to 1. We are yet to prove it in the case of 1 by 2 to 2 by 3. The current result is this. Basically, these are constants, and this, if you recall, is the M is the set of adversarial nodes. So MC is basically the set of non-adversarial nodes. Basically, if you have more adversarial nodes, more non-adversarial nodes, it converges faster. That is intuitively proved from the inequality. So basically, we have computed this in a case where A lies between half 2 by 3 and 1. In that case, we have almost sure convergence. In the half to 2 by 3 range, we do not have almost sure convergence, but we do have the expected value convergence. So we are yet to complete this. The work is going on, we should be done soon. But we have, so far we have obtained the best convergence rate of n power 1 by 3. Basically put a 2 by 3 in this to get 1 by 3. That's the best we have so far. We still need to get to big O of 1 by root n. I have discussed an example here. Basically, this was one of the lists we showed in the previous example as well. So the original, so this is the original here, the blue curve basically. Blue goes here. The orange is n power a minus 1, this value. So that's here. When you divide these two, if you want this to be the exact convergence rate, this should approach a constant value. If it approaches 0 faster, then this convergence rate is stronger than the actual convergence rate, and if this approaches infinity, it means that it does not convert as fast as that one. So basically, this approaches a constant value. This is basically like what? 16 lakh data points. After 16 lakh iterations, this took like 25 minutes to run on the computer. So after that much time, you have a constant value. So like yes, this is the expected convergence rate we have. We have not completed the proof yet. Questions?
What about the number of adversaries? Will the convergence for no matter how many adversaries?
No. That's what I discussed. So yeah, you do not have convergence in this case if you have 3 adversaries.
So in the formula, how do we reconcile the process?
There is a condition on the adversaries. I have not written it here, but there is a convergence on how many adversaries you can have.
So what is the approximate number?
I don't know, it's around, say you cannot have, say, maybe it's less than half for sure, that is pakka, but you cannot have, say, in this matrix you cannot have more than 1. This one you cannot have more than 2. So it's around like 30-40%, at least amongst the examples we have seen.
Is it an empirical bond or a proven bond?
It's a proven bond.
So it goes like a fraction. Like it is theta of n, you're saying, the bond.
It is?
The bond on a number of adversaries is theta of n.
Yes, it is.
Okay.
Yeah, any other questions? Third. Okay.
Discrete time.
Basically, it's not continuous. So you look at 1, 2, 3, so on. You don't look at say 1.5 or 2.3. Those are not the times you consider. You just look at 1, 2, 3, so on. So basically, so in this graph you obtain, there are too many data points here. That's why it looks like a perfect continuous graph. If I restrict it to something like 50 data points or something, you would have observed something like you would observe in capstone, like just straight lines connecting the respective points. Any other questions? You can ask questions about the PPT or about my project. Either is fine. Like in general, like what kind of projects you can get at CSA. That is all.
What about Saurav's question about the adversaries?
Sorry?
The motivation for adversaries.
I'll attach it. It's something you have to read. No other questions? Thank you.
So our next speaker is Akash from the third year. He will be speaking on Fourier series.
So hi everyone, I am Akash. I am third year undergrad here. My different project is Fourier analysis with Arkamani sir this summer. And this talk will be a basic simple introduction to Fourier series. I hope it will be very beneficial for everyone, and I think even the second year undergrads can also follow. I have to play some videos. Let's look at a simple animation here. What you are looking at right now is a complex Fourier series. And in this talk, we are going to understand the maths behind it. As you can see, there are many linear vectors which are merely just rotating at a constant frequency, which have been added tip to tail, and the final tip of the sum draws out a drawing for us
like an artist. We can look at more examples here. This is the example of the summation symbol. Here is a complicated map of Euclid, and it was Joseph Fourier who had introduced this idea of representing functions as a sum of sines and cosines, which today has so many applications in wide fields. So he had presented this idea in his paper on heat equation. So let's look at the heat equation and try to find where he found his motivation for this brilliant idea. So this is the heat equation. We have all seen it. Sigma and kappa are just some constants. The U represents the temperature at coordinate x and y and at time t. So many mathematicians in the 18th century were interested in how the heat evolves or how the temperature distribution evolves in a solid with time. Or if we fix the temperature on the boundary of a plate, what would the heat or the temperature distribution on the plate would look like after a long time? So we are going to look at that example. So we know that after a long time equilibrium will be reached. So the left hand side will equal 0 and the right hand side can be simply written as the Laplacian of u equal to 0. So let me state the problem formally. We have a unit disk D, it has a circumference c. We are working in the polar coordinates form, r and theta, and we have fixed the temperature on the boundary. Let's say it is given by f of theta, the temperature distribution on the boundary. So here the Laplacian has just been represented in the polar coordinates form, and after some simplification you can see it reduces to this. Now my question for you is, what should be our next step from here? OD people, if you remember,
Separation of variables.
the next step is variable separation is the way to go. So we assume that our solution is a product of two functions. Each function is a function in the independent variable r and theta. We substitute it here and we get a simpler form. Now the left hand side and the right hand side are functions in independent variables, and if they are equal, then they must be equal to some constant, say lambda. So now we have successfully converted our PD into two simple ODEs, and now observe that G is a function of theta, so it has to be periodic into pi. So our lambda has to be non-negative. Let's say it is equal to L square. So if you don't recall the solutions to these, you can verify that e to the power plus or minus in solves this ODE, and r to the power plus or minus n solves this ODE. So my next question is, why do we need to discard r to the power negative m if we assume m is greater than 0? If you imagine r to the power negative m is unbounded at the origin and it won't exist the realistic situation. So we only look at solutions by taking modulus of m. So we found solutions un for a parameter m. And because the PD was linear, we can add our solutions to get another solution. So a general solution can be written as a linear combination of all the solutions we found. So this is written here. So if we get one more boundary condition, that we have fixed the temperature on the boundary given by f theta. So that gives us this expression. And now we can ask, how can we find this coefficients En from this infinite series? A similar expression is also obtained when we are solving for steady states of a vibrating string like this. So these expressions have created many doubts and questions in the minds of 18th century mathematicians, like, can any arbitrary function can have such expansions? Is continuity alone enough to say that it will have such expansion? And what classes of function would have such expansions, such Fourier expansions? And if it does have, how do you find these coefficients, the Fourier coefficients? So many mathematicians just did work assuming that arbitrary function has such expansion. Even Euler was unsure that is it really true any arbitrary function can have such Fourier expansion. So it was the work of Joseph Fourier on heat diffusion which helped so many mathematicians to complete their proof. So Now we will take a brief look at the maths of the Fourier series. So let's start simply. We look at some classes of functions. Everywhere continuous functions, as the name suggests, they are continuous everywhere. Piecewise continuous functions, they are continuous in pieces, and they can be discontinuous only at finitely many points. Riemann integrable functions, simply you can easily integrate them, but they may be discontinuous at infinitely many discrete points that you can still evaluate the integral. So periodic functions. So Fourier series is used to approximate periodic functions, and we are all familiar with it. A periodic function would satisfy an equation like this: f of x plus n equal to f of x for all x belonging to its domain. So such functions are called L-periodic. Here are some examples of 2-pi periodic functions like sine nx, cos nx, e to the power inx, and square waves, which you would remember from your electronics lab. So now we come to the main crux. A Fourier series of a 2-pi periodic function can be formally written as this infinite sum, where these Fourier coefficients are given by this expression. You can see that this relates to the Fourier strips which we had learned in physics. So also, if your function was L-periodic, then its Fourier coefficient is given by this big expression. But to simplify our calculations ahead, we will just assume that our functions are integrable and they are 2-pi periodic. So let's take a simple example of a discontinuous function, the sawtooth function. The function is like this. Then here, then here. You can see it has very sharp discontinuities. So you can easily evaluate its integral, and you will find its Fourier series is given by this infinite sum. So you can understand this infinite sum as the limit of a partial sum, and the partial sum converges to your function, discontinuous function, as you take more and more terms. So let's try to see through this animation. Here we have taken just one term. It doesn't look like what we want, but you can see as we take more and more terms, it starts to take some shape. So you can see as we increase the number of terms, the approximation to our function gets better and better. And in the limit of infinite, it will actually equal the discontinuous function. So you can see better and better approximations we can get like this. Now I had defined the 2-pi periodic function Fourier series formally, because I had not talked about where this infinite sum converges. So let's take some look at some convergence theorems. By the way, this is the partial sum I was talking about. Minus n to n, you can take the sum. And functions on a circle are simply functions which you define on 0 to 2-pi, which have equal values on the endpoints. So like their values loop around. So you can say they are functions on the circle. So let f be an integrable function on the circle which is differentiable at a point theta 1. Then the Fourier series converges to the function at theta 1. So this is a pointwise description, a local result. If your function is differentiable here, the Fourier series converges here. If your function is differentiable everywhere, then your Fourier series converges to f at each point. So it is a pointwise convergence description. And the rate of convergence may be different at each point. So if your function happens to be twice continuously differentiable, meaning that the second derivative of your function is continuous, then your Fourier series converges absolutely and uniformly to f, meaning that it still converges at every point, but the rate of convergence is uniform. So the proof simply goes, you get an approximation on this Fourier transform by some constant times 1 over n square, and we know that this series has to converge, so this series converges absolutely and uniformly. So finally, I want to ponder on one question which would have struck many mathematicians in the 18th century. How can a sum of infinitely differentiable functions e to the power I and theta be equal to a discontinuous function. So, discontinuous function. So, we know that if we take a partial sum, it will still be infinitely differentiable. But Fourier was venturing on infinite sum, and there are numerous examples in mathematics which show that infinite sum can bring some qualitative changes to your expression. Like in the Bessel's problem, you take infinite sum of rational numbers and you get an irrational number here. So are these two ideas, one in Fourier and one in number theory, related? So surprisingly, it turns out if you take the simplest example from your high school of a function like modulus of theta, and you evaluate its Fourier series and just merely evaluate the value of this at theta equal to 0, you get a solution to your Bessel's problem. So this is just a small illustration what Fourier series can do, and why it has so many applications in mathematics, in algorithms, and in signal processing. In algorithms, we are studying about fast Fourier transforms, and it has so many applications in it. So finally, I want to ask someone, can anybody guess how this animation would have been made? What is the length of these vectors which are rotating at some frequency n? So as you saw, the coefficient was f of n, the Fourier transform, and you just define a function on the complex plane which draws the smoother version of the symbol that you want. You evaluate its Fourier series and just plot the infinite sum on an animator. So thank you everyone.
Thank you. So our last speaker for today is Saurabh from Australia, and he will be speaking on rational cryptography.
Hello everyone, I'm Saurabh Peruri. I'm a third year math major. I did my summer project under Bhavana Karukurti in CSA department. She is working on cryptography and in particular rational cryptography. And yeah, I'll explain you more about cryptography and game theory, and I'll end it the place where I started my project at. So first of all, let's talk about cryptography. So in cryptography, there's a problem called MPC, multi-party computation. So the setting for the problem is as follows. You have parties pi, where I is from 1 to n, and all of the parties want to evaluate a function f. So each party pi has an input ti, and the function is basically, the function takes as inputs each party's input and returns an output. So the setting is that the parties want to compute the joint output S, which depends on all of their inputs, but the cryptographic restriction here is basically that the parties cannot know about during the process of computation of this function, the parties cannot know about anything except what can be learned from Ti and S. Basically, it is saying that apart from what you can learn from Ti and S, each party Pi is not going to. This is the restriction. Each party Pi should not learn anything about the function or other people's inputs. So this is the setting, and obviously if you remove the cryptographic setting, every party PI can just broadcast their inputs, and each party, since they have the knowledge of the function f, so each party can just evaluate their function locally and then get the output as. It is the restriction that makes the problem interesting. So yeah. So how do you go about doing this? So in an ideal world, you can have a mediator, say M, who's a trusted mediator, who each party trusts, and all the parties privately send their input Pi to M, and M computes the function f and returns the output S to everyone. Note that there's a generalization of this problem where S is a vector of outputs, and each party receives their own output Ti and Ss. So it is easy to see intuitively that the trusted mediator implementation of this problem is secure, because the trusted mediator, I mean, there's an agreement that the trusted mediator does not disclose any information, and they compute the function T, like f of T1 to Tn, and they return the input, return the output Si to each party individually. Now, the security definition, in cryptography, security definitions are very important, and there are a lot of nuances involved. So I am not going to go into the definition of like a secure multi-party computation protocol, but it is like intuitively saying that any protocol which computes f in this fashion has to have an identical how do I put it? It has an identical sort of run as it happens in like an ideal world. So the actual word for it is transcript. So like the interaction in the protocol, when the parties have to interact to get the like desired output, they generate a transcript, and the definition essentially says that the transcript is identical in the real and ideal cases. I'm not going to go into much details about it, it's just a nuance. But yeah, so most existing protocols for MPC actually rely on something called secret sharing. So let me talk about secret sharing. The setting for secret sharing is that you have a secret, say Z, and you want other people, like you want to give out your secret Z to other parties, and you don't want any other like you want the parties to sort of collaborate so that like they get to know the secret together, and it shouldn't be a case that one party learns about the secret by itself. I'll just explain it to you, it will be clear. So what a secret sharing scheme is that there is a dealer which takes the input as the secret Z, and it splits it Z into shares. So it is split into n shares, and each share is handed to one party. So Zi is given to Pi, and this is the distribution process. Now the reconstruction process of the secret sharing scheme basically involves the parties coming together, and they just join all of these parts together and get back the secret. So there is something called K, N secret sharing scheme, where a secret, an input basically, is split into n parts, and if K or lesser parties come together, they cannot get the secret, But if any set of k plus 1 or more parties come together, they are able to reconstruct the secret. Now, okay, this might all feel a little like what do you mean creating a secret and what is a secret and all. So I'll just give you an example. It is called Shamir secret sharing algorithm. It is as follows. You suppose your secret is Z, which lies in some field F. This is a value which lies in the field F. What you do is you construct a polynomial in that field F with the degree k, with the only restriction that f of 0 is Z. So here f is a randomly arbitrarily constructed polynomial of degree k whose free coefficient is basically Z. Now what shares you give are essentially f of alpha 1, f of alpha 2, f of alpha n, where alpha 1 to alpha n are some pre-agreed non-zero, obviously non-zero values. Now you can easily see that if k or less people gather, they will have like k values of these n values, and they won't be able to reconstruct it. But as soon as there is one more k plus 1 party, you will have k plus 1 values, and you can interpolate to get the polynomial, and you can evaluate the polynomial at 0 to get your secret set. So is this clear? Or should I go over it once again? Okay. So this is a secret sharing scheme. Now I will briefly describe how an NPC uses secret sharing scheme. So I will need a matrix. This is just for your understanding. Say each party, sorry, not this. Each party PI has its input TI, right? So what the protocol, what most general MPC protocols do is split this PI into n shares and give one share to each of these parties. So it will be TI comma 1 for notation purposes till TI comma n, and each party does that. So T1 comma 1, T1 comma n, so on. And these, so my row represents what information, so the first row represents what information P1 has. It has T1 and the shares of all T1, and similarly each party PI has TI and their shares. Now what my column represents is what information they get in the end. So that would be, say P1 would get the first share of all the inputs. That is clear, right? And the I party would get ith share of all the inputs. Now, this is a nuance again. The function can be evaluated using a circuit which sort of preserves this form of secret sharing, preserves the representation. So, if even if you input the first shares of all of these, you will get a valid share of the output. You get what I mean, right? Basically, you get valid shares of your outputs, and each party locally computes F on their on the shares that they get. These shares are from all inputs. Now, this is there's one more step left. You have shares of a valid output. Now, the parties come together, they broadcast. By broadcast, I mean simultaneously announce. They broadcast their outputs, the shares of the output, and they're able to reconstruct the output. That's clear? So, this is an introduction to multi-party competition. Can I know how much time we have?
We have 10 minutes.
Next, I'll be moving to game theory and I'll define what a game is. And yeah. So, a game, specifically a one-shot game, in which basically there is one round and all players play simultaneously, is the following. It is a set I. You can think of it as an indexing set. And then it is a, like, okay, I'll just try it out. So it is a tuple which has a set I. Say the set I is basically indexing the parties, and for each I there is a set SI. SI is called the action set or the strategy set of party PI, and UI is the utility function which I'll define. So think of SI as what moves the player PI has. So UI is a utility function which takes an input from S1 cross till Sn and outputs a real number. So how do you think of it? So each element from this set pi s, now I'll call pi si as s from now. So each element of this set s basically represents each party simultaneously choosing a strategy or an action from their action set si. Is that clear? Every element of S essentially is an outcome. An outcome is basically that, like, okay, I'll just. So, a small s is small s in S is of the form S1 to Sn, where each Si lies in the bigger, like the set Si. And it is a strategy or an action that the party takes. Okay, and for all I, the utility function assigns each outcome or each strategy. This is called a strategy profile. By the way, I will refer to this vector as strategy profile. So UI for each I assigns each strategy profile with a real number. Now these real numbers are taken and are they are taken to be indicative of their preferences. Like, say if you are playing a game of heads and tails, and I win if I get a heads, then my UI of my utility for the outcome heads would be higher than my utility for the outcome tails. Okay. So utilities essentially give you an understanding of what the player prefers to.
Can you clarify what the product is using in the definition of UI?
Here, it is basically this strategy sets or action sets S1 is the product of all those sets.
S1 to SI.
S1 to Sn. So, like each player has their own utility function. Say for the same outcome, if you and I are playing game of heads and tails. If I win when I get heads, then you obviously will lose when you get heads. So my utility function would be UH greater than UT, but your utility function would be something UH is less than UT.
So I is indexing over the players.
Yeah, I is indexing over the players. Okay. So now I'll quickly tell you what Nash equilibrium is. it deserves much more time than what I can give right now, but yeah. So now an equilibrium is basically consisting of a strategy profile which is stable. A Nash equilibrium basically says you call S star a Nash equilibrium strategy profile if for all I ui of Si star okay, I need to clarify on some notation. If this is S, it has obviously Si. I'll denote with S minus I the following tuple. So it is everything but Si. Okay, it is the strategies of every other player except Si. So S minus I refers to this tuple. So here Si star and S minus I star is essentially S star. Okay, but what Nash equilibrium states is that for all I, this thing on the left hand side is greater than or equal to for all Si belongs to capital Si. What it is saying that if and this is an important clause, if every other player follows their Nash equilibrium strategy, which is reflected by this part being the same on both sides. If every party except I is following their Nash equilibrium strategy, then it is most beneficial to you if you also follow Nash equilibrium strategy. That is reflected by varying Si over all possible strategies that a person can take, and the utility function and its inequality are there to represent the preference of the outcomes. So and this is for all I. So if you are a player, assuming that everybody else plays your Nash equilibrium strategy, you would be, it would be in best interest to you to also play the Nash equilibrium strategy. This is what Nash equilibrium is. There is a stronger concept of equilibrium called dominant strategy equilibrium. I will modify this one. S star is a dominant strategy equilibrium profile if all the strategies S1 to Sn star are dominant. And by dominant, I mean the following. That even if the other parties don't stick to Nash equilibrium, their Nash equilibrium, basically even if the other parties don't stick to this profile, still it is in best interest to you to play the dominant strategy profile. Such a strategy profile is called dominant strategy profile, and the equilibrium where everybody plays this outcome, plays this strategy is called a dominant strategy equilibrium. Is it clear the difference between Nash equilibrium and dominant strategy?
You have 2 minutes.
Okay. Now, I'll go over one famous example. I'll read more there. So, this is the prisoner's dilemma that I'm going to tell you about. Imagine the police arrests 2 people for a crime, but the police does not have enough evidence to put them in jail. So what the police tells each person individually is that, so NC and C are basically not confess or confess. So each player has two choices: to not confess or confess. And what the police tells each player is that if you confess to the crime but the other person does not, then you walk free but the other person faces 10 years in jail. So in each box I am going to write a tuple which is basically U1 comma U2. So in each box there will be two entries, and each entry, the first entry will be U1 of NC comma NC. So here what will go is U1 of NC comma NC, here U2 of NC comma NC, and so on. I hope the notation is clear. You will check it. So what the police says is that if both of them confess, then they'll get 5 years in jail time. Since we are maximizing utility, I am assigning -5 so that they minimize the amount of jail time. So I'll just fill this up. So if both of the prisoners decide to not confess to the crime, then they'll get 1 year in jail. But if one person confesses and the other does not, the person who confesses walks free, but the person who does not faces 10 years in jail. And it's the same, so it's just basically a reflection. Okay. So is the setting clear? Now we'll analyze the equilibrium here. If you see, assume person P2, prisoner P2 chooses to not confess. That is, P2 chose NC. So let's see what P1 should choose. Now P1's utility is the first entry. So it is in.
Will you solve the offenders?
Okay. Okay. This is missing. So this is person P1. I just interchange the labels. Now, if P1 chooses to not confess, let's see what is in best interest for P2. P2's utility is in the second entry. So, comparing -1 and 0, you will see that P2 would like to confess, because that would give P2 an edge over choosing to not confess. Let us see what happens if P1 chooses C. -10 and -5. Obviously, -5 is greater than -1. So, regardless of what P1 chooses, P2 would like to choose C to confess. And since this is a symmetric thing, both people end up confessing and they face 5 years in jail together. This is a dominant strategy equilibrium because you can verify with the definition. Now, if you see, there is an obviously much better choice for both the parties to choose. But since this is non-cooperative and you don't know what the other person will end up choosing, this results in this. But I mean, can this equilibrium be achieved somehow? Can you enforce this equilibrium? And the answer is yes, but it is a different kind of equilibrium. It's called correlated equilibrium. So, in correlated equilibrium, okay.
Year over time.
Okay, just 2 more minutes. I end in 2 minutes. So, think of forget correlated equilibrium. I'll tell you, let's just take a digression. Now, say there is a mediator M along with the parties, and the mediator takes as input S. So assume the parties choose a strategy, and mediator M basically takes as input all of their strategies, and then the mediator processes it and privately recommends some other strategy to each party. It need not be some other strategy. Say it takes as input SI, it gives the output to each party as some SI, say some TI. Okay. So the mediator says I mean, if you tell the mediator, hey, I'm planning to play SI, the strategy SI, the mediator says, maybe you should play TI. TI can be SI or TI and anything else. Now, the purpose of introducing this is maybe the mediator can somehow tell them both to play -1 and -1 and it works out. So, like on this lines, a correlated equilibrium is defined as the following. An equilibrium strategy profile. A strategy profile is called a correlated equilibrium strategy profile if mediator basically, like when you give it as the input to the mediator gives like the action that mediator recommends is in best interest to you. In a sense, like when I actually define mediator, you don't know what the mediator can do. You just hopelessly trust them, so that they trust them to give you a better action. In case of correlated equilibrium, what the mediator ends up doing is give a strategy to each party which is actually beneficial to them, and which is better than all other strategies, so to say. Now, I mean, this is a high-level overview and it's not at all rigorous, but now one aspect of cryptography actually revolves around removing. I mean, the mediator. Look at the similarities between the mediator M and the MPC problem that I stated earlier. They take an input of all the parties and they give an output, which is the same, again an action. So a part of the research in cryptography and game theory revolves around implementing a mediator using an MPC protocol. So that is one aspect of cryptography and game theory, the intersection of cryptography and game theory. Another aspect is actually something called rational secret sharing, or rational rational MPC protocols. In one more minute, I'll tell you just one. So the secret sharing scheme that I told you earlier, it is actually not rational, in the sense that if all the players in the who are participating are rational, they would want to maximize two things: correctness and exclusivity. Correctness, basically that they get the correct output. Basically they get the correct secret, and exclusivity saying that if they get the secret but other parties don't get the secret, that is preferable, which is reflected in the utility functions. So rational secret sharing scheme is a secret sharing scheme where even if the parties are rational, it is in best interest for them to follow the protocol as it is. Now I'll tell you why the Shamir algorithm is not rational. Imagine if exactly imagine if exactly k people participate in the secret sharing scheme. Then so you have n parties all gathered around and k of them broadcast their shares. So you will have their k shares and you will also have your own share, which other parties don't know. So you will have k plus 1 shares and nobody else will have, right? So you will be able to reconstruct the secret, while the parties who announced won't be able to reconstruct the secret. So you would prefer to keep quiet, right? You would prefer that other people broadcast their shares and expect that you are able to reconstruct the secret. So you would prefer to keep quiet. But since every player is rational, everybody would keep quiet and the protocol won't follow. So this is rational secret sharing scheme, and rational MPC is what I looked at in the summer, and you can contact me if you afterwards if you're interested.